in the vast silent theatre of space, the greatest war ever fought began before a single star ever ignited. It is a conflict that has raged for 13.8 billion years, from the very first whisper of creation to the supermassive black holes that lurk at the hearts of galaxies today. But this war is unlike any you have ever imagined. There are no trenches, no fleets of ships, no blaring alarms or desperate radio chatter. This war is fought with gravity, with radiation, and with the slow, relentless crush of time itself. The weapons are not bombs or lasers. They are light, heat, and the invisible, inescapable pull of mass. The soldiers are clouds of gas, clumps of dark matter, and the titanic stars that burn their way across the cosmic stage. And the battlefield is not a planet or a system. It is the entire universe. To understand this invisible battlefield, we have to go back to the beginning, not to the Big Bang itself, but to a moment just 380,000 years later. At that time, the universe was a seething, opaque soup of plasma. It was so hot that electrons could not bind to atomic nuclei. They just bounced around, slamming into photons, scattering light in every direction. The universe was, effectively, a glowing fog. But then, something remarkable happened. The universe cooled down to about 3000 degrees Kelvin. For the first time, electrons and protons could finally link up, forming neutral hydrogen and helium atoms. As they did, the fog lifted. The universe became transparent. And for a brief, glorious moment, it was filled with the faint afterglow of creation, a light that we now call the cosmic microwave background. But then came the silence. For 150 million years, the universe plunged into absolute darkness. Astronomers call this period the cosmic dark ages. No stars, no galaxies, no planets, no light at all. Just a vast, cold, expanding void filled with neutral hydrogen and helium gas, and something far more mysterious, dark matter. To imagine it, think of the most remote, lightless cave you have ever been in, and multiply that feeling by the entire cosmos. The only actors in this play were two forces. One was dark matter, the invisible scaffolding of the universe, clumping together in ways we still do not fully understand. The other was gravity, ancient and patient, beginning its slow, delicate work. Gravity started pulling at the faint density fluctuations left over from the Big Bang. Tiny regions where there was just a fraction more matter than average began to collapse upon themselves. It was like a gigantic game of cosmic capture the flag, and gravity was the only player. And this right here is the origin of the conflict. In the early universe, gas and dark matter were everywhere, but they were not evenly distributed. Some regions had a little more mass. Those regions pulled in more material, and as they pulled, they grew denser. As they grew denser, they pulled even harder. This runaway process is called gravitational collapse, and it is the engine that drives the entire Cold War of the cosmos. But here is the thing. Gravity is not the only force in town. As that gas collapsed, it heated up. Compression does that. So you had gravity pulling inward, trying to crush everything into an infinitely dense point, and you had thermal pressure pushing outward, trying to expand the gas cloud back into space. It was a standoff, a tug of war between opposing cosmic forces, and for millions of years it was a stalemate. But eventually, in the densest, darkest pockets of space, gravity began to win. The gas clouds collapsed further and further until their cores reached incredible pressures and temperatures. And then, around 200 million years after the Big Bang, something truly spectacular happened. The first stars ignited. These were not the gentle yellow suns we know today. These were monsters. Astronomers call them population 3 stars, and they were absolute behemoths. Each one weighed between 100 and 300 times the mass of our own sun. They burned so hot, so bright, that their surfaces reached temperatures of over 100,000 degrees Kelvin. That is more than 15 times hotter than the surface of our sun. They glowed a brilliant, blinding blue-white light, so intense that it could strip electrons from atoms thousands of light years away. But here is the tragedy of these first stars. They burned fast and they burned young. A star like our sun will happily fuse hydrogen into helium for 10 billion years, slowly and steadily. But a population 3 star, a monster of 300 solar masses, lived fast and died young. Its core burned through its entire fuel supply in just 3 million years. 3 million years. That is a blink of an eye in cosmic terms. When it died, it did not go quietly. It did not puff out a pretty planetary nebula. It exploded as a hypernova, a blast so powerful that it outshone an entire galaxy of 100 billion stars. That blast scattered the star's heavy elements, carbon, oxygen, iron, silicon, across the surrounding space. These elements were the seeds of everything that would come later. The planets, the moons, the life, the us. It all came from the death of these first stars. And that death changed the battlefield forever. You see, before those first stars exploded, the universe was composed almost entirely of hydrogen and helium. Gas clouds could not cool down easily. They were stubbornly hot. But when those hypernovae seeded space with heavy elements, the rules of the game changed. Heavy elements are incredibly efficient at radiating heat. They act like cosmic radiators. A gas cloud that contains a tiny fraction of carbon or oxygen can cool down to just 10 degrees Kelvin above absolute zero. 10 Kelvin, that is colder than anything on Earth. And when gas clouds get that cold, they collapse faster. Gravity suddenly had a much easier job. The Cold War between gas pressure and gravity now tilted heavily in favour of gravity. These cooled, heavy element-rich gas clouds became the true nurseries of stars. But do not let the word nursery fool you. They were not peaceful places. They were contested zones, battlegrounds, where forces clashed on scales we can barely comprehend. Imagine a giant molecular cloud, hundreds of light years across, filled with cold, dense gas. Gravity is pulling it inward, trying to break it up into thousands of collapsing cores that will become new stars. But radiation from those newborn stars pushes back. Intense ultraviolet light heats the gas, ionizes it, creates bubbles of high pressure that resist further collapse. Stellar winds, supersonic streams of charged particles, blast outward from young stars, carving cavities in the cloud. And then there are the supernovae. When the most massive stars in the cloud explode, they send shock waves ripping through the gas, compressing some regions and blowing others apart. It is chaos, beautiful, violent, and chaotic. These molecular clouds are the front lines of the Cold War. Within them, gravity and radiation fight for dominance. Gravity wants to build stars, massive clusters of them, dense knots of matter that will one day become galaxies. But radiation and supernova feedback want to destroy the cloud, to disperse it back into the interstellar medium, to prevent gravity from having its way. This is the fundamental conflict that has shaped the universe for the last 13 billion years. It is the reason that galaxies do not form all their stars at once. It is why star formation is so inefficient, converting only a few % of a cloud's mass into actual stars. It is the reason we have the beautiful, varied, complex cosmos we see today, instead of a universe full of supermassive black holes and nothing else. But the war does not end there. Look deeper into the heart of these collapsing clouds. The forces at play become even more personal, even more intimate. A tiny fluctuation in density, a region where gravity is just slightly stronger, begins to pull in more gas. As it collapses, it spins up, conserving angular momentum, forming a rotating disk. In the center of that disk, a protostar is born, but it is not alone. In the disk, clumps of gas and dust begin to form, planetesimals, the building blocks of worlds. And here again, the battle resumes. The protostar is blasting out radiation and jets of magnetically accelerated plasma. It is literally trying to blow away the disk from which it formed. If it wins, it clears out the debris and no planets form. But if gravity can hold the disk together, if the material can resist the stellar wind, then planets form. And when planets form, we get worlds, we get atmospheres, we get oceans, we get life. This is not a peaceful process. Planets collide, scatter, and merge. Impacts reshape entire surfaces. The young star's radiation can strip a planet of its atmosphere, leaving it barren. Or it can warm the planet just enough to sustain liquid water. Every step of the way, it is a negotiation, a constant push and pull between creation and destruction. And that is why this Cold War, this invisible battle between gravity and radiation, is the most profound conflict in the universe. It is not just a story of stars and gas. It is a story of how everything we know and love came to be. It is a story of how order emerges from chaos, and how chaos constantly tries to tear it all down. So, as we look up at the night sky, at the pinpricks of light that dot the darkness, remember what you are seeing. You are seeing the front lines of a war that has been raging for nearly 14 billion years. Every star you see, every planet that might orbit it, every molecule in your own body, is the product of this cosmic conflict. Gravity pulls, radiation pushes, and stars annihilate their own cradles. It is a delicate, violent balance, and so we have to ask ourselves, what happens next? Who wins? Does gravity eventually overcome all resistance, pulling everything into an endless, silent darkness? Or does radiation win, blowing all the gas and dust away, leaving the universe a cold, empty, starless void? Or perhaps, just perhaps, the answer is that neither side ever truly wins. Perhaps the fight itself, the Cold War between stars, is what keeps the universe alive. So where does that leave us? Staring into the abyss of a cosmic nursery, wondering if gravity will quietly win the day, pulling everything down into an endless, silent darkness? Or does radiation win, blowing all the gas and dust away, leaving the universe a cold, empty, starless void? Or perhaps, just perhaps, the answer is that neither side ever truly wins. Perhaps the fight itself, the Cold War between stars, is what keeps the universe alive. But to understand why that fight is so brutal and so beautiful, we have to look closer. We have to strip away the pretty pictures and dive into the raw, hard data. We have to talk about the stage where this war is fought, and that stage is the giant molecular cloud. You have probably seen the Orion Nebula. It is that fuzzy smudge in the sword of the constellation Orion, visible to the naked eye on a clear winter night. Through a telescope it looks like a glowing, wispy cloud of gas, a kind of cosmic cotton candy. But that is just the tiny, lit-up surface of something far, far bigger. Behind that glowing curtain lies the Orion Molecular Cloud Complex. This thing is a monster. It sits roughly 1,344 light-years away from Earth, which sounds far, but in galactic terms, that is practically in our backyard. And it is huge. I mean, really huge. This cloud spans about 500 light-years from one end to the other. To put that in perspective, light itself takes 500 years to travel from one side to the other. Our entire solar system, from the Sun all the way out to the Oort cloud, is about 2 light-years across. This one single cloud is 250 times wider than that. It contains enough gas and dust to make thousands of stars just like our Sun, and that is just one cloud. There are thousands of them scattered throughout the Milky Way, each one a massive, cold, dark factory for stars. They are called giant molecular clouds for a reason. They are enormous, and they are full of molecules. Mostly hydrogen, of course, molecular hydrogen, 2 atoms stuck together. But hydrogen is a shy molecule. It is incredibly hard to detect directly, because it does not emit radio waves easily at the cold temperatures of these clouds. So astronomers rely on a different tracer. They use carbon monoxide, a simple molecule, 1 carbon atom and 1 oxygen atom, but it is a much better communicator. It lights up in the radio spectrum like a beacon. When we map the sky for carbon monoxide emission, we see these clouds in all their glory, vast, dark, sprawling structures that snake across the galaxy. But even though they look huge and dense in our radio maps, the reality is almost impossible to grasp. These clouds are cold, bitterly, brutally cold. We are talking about temperatures of 10 to 30 Kelvin. That is minus 260 degrees Celsius. That is colder than the surface of Pluto, colder than the average temperature of deep space. In fact, it is just a few degrees above absolute zero, the point where all atomic motion theoretically stops. Atoms and molecules barely move. They just kind of huddle together, frozen and still. Yet, despite that bone-chilling cold, these clouds are still a near-perfect vacuum. The density inside a giant molecular cloud is about 100 to 1,000 particles per cubic centimetre. That sounds like a lot, but on Earth, the air you are breathing right now, has about 10 to the 19th power molecules per cubic centimetre. So, a cubic centimetre of space inside one of these clouds is trillions of times emptier than the air in your room. It is a better vacuum than anything we can create in our most advanced laboratories on Earth. So it is cold, it is dark, and it is almost completely empty. And somehow, from this seemingly sterile, frozen void, stars are born. For decades we thought of these clouds as big, smooth, uniform blobs of gas. They were the cosmic equivalent of a quiet, still pond. But then we got better telescopes. We pointed the Herschel Space Observatory at the sky in 2010, and what it saw changed everything. It revealed that these clouds are anything but smooth. They are clumpy, they are messy, they are violent. Herschel showed us that giant molecular clouds are woven from an intricate network of filaments. Think of them as cosmic spiderwebs, but instead of silk, they are made of cold gas and dust. These filaments are long, thin threads of material that snake through the cloud. A typical filament is only about 1/10 of a light year wide. That is about 600 times the distance from the Earth to the Sun. It sounds vast, but compared to the cloud itself, it is a hair-thin strand. And these strands can stretch for dozens of light years, winding their way through the darkness like rivers in the sky. And here is the stunning discovery. Herschel found that nearly every single star in the universe forms along these filaments. Virtually 100% of star formation is happening on these narrow, dusty threads. It is not a random process. Stars do not just pop up anywhere in the cloud. They form along the filaments, and specifically, they form at the intersections where two or more filaments cross. It is like the frayed ends of a rope, where the threads are weakest. At these junctions, the density of gas and dust spikes dramatically. Material starts to pile up. Gravity feels the increase in mass and starts to pull harder. These intersections become the wombs for new stars. You have probably seen the most famous example of this, the pillars of creation in the Eagle Nebula, those iconic elephant trunk-like structures of gas and dust reaching out into space like the fingers of a giant hand. You have seen the Hubble image, the one that looks like a fantasy landscape. Those pillars are essentially giant filaments. They are dense columns of gas that are being sculpted and eroded by radiation from massive stars just outside the frame. And in those pillars, buried deep in the densest knots, new stars are being born. You can see them if you look at the Hubble image in infrared. The pillars appear to glow from within, lit up by the infant stars that are still hidden inside their cocoons. It is a cosmic nursery under siege. The radiation is trying to tear the pillars apart, while gravity is trying to pull the gas inward to form stars. But that brings us to a massive problem. A paradox, really. We have known for a long time about something called Jeans instability, or Jeans criterion. It is a simple equation named after the British physicist James Jeans from the early 1900s. It tells us that if a cloud of gas is massive enough and cold enough, gravity should overcome the internal gas pressure, and the cloud should collapse. It should just fall in on itself. And for a typical giant molecular cloud, the Jeans criterion says that the collapse should happen in about 100,000 years. 100,000 years. That is a blink of an eye in cosmic terms. That is nothing. Given that our galaxy is over 13 billion years old, 100,000 years is like a single heartbeat in a human lifetime. So if the Jeans criterion is correct, these clouds should collapse and form stars almost instantly. But when we actually look at the Milky Way, we see something very different. Star formation is happening, but it is incredibly slow. It is about 100 times slower than what the Jeans criterion predicts. The clouds should have collapsed long ago, but they are still there, sitting in space, just hanging out. Something is stopping them. Something is resisting gravity. Something is holding the pieces back. What is that something? It is not one single force. It is a team of them. It is a three-way standoff. The first force is turbulence. When we think of turbulence, we think of a bumpy airplane ride or whitewater rapids, but this is turbulence on a galactic scale. The gas inside these clouds is not still. It is churning, it is swirling, it is moving at hundreds of thousands of kilometers per hour in chaotic random directions. It is a supersonic maelstrom. This turbulence creates shock waves, which pile up gas in some places and rip it apart in others. It prevents the gas from settling down and collapsing under its own weight. It is like stirring a pot of water so fast that the bubbles never have a chance to form. Turbulence is the cosmic agitator, and it is incredibly effective at stalling star formation. The second force is magnetic fields. The space between the stars is threaded with a weak magnetic field. It is a ghost of a field, perhaps 1,000,000 times weaker than the Earth's magnetic field. But because the clouds are so huge and so diffuse, even a weak magnetic field can have a huge effect. The ionized gas in the cloud, the charged particles, they feel the magnetic field lines. They get stuck to them like beads on a wire. As gravity tries to pull the gas inward, it has to drag the magnetic field lines along with it. But the magnetic field resists. It acts like a spring. The more you try to compress the field, the harder it pushes back. This magnetic support, this tension, is a major force that holds the cloud up against collapse. It is like trying to collapse a balloon filled with air. You can push, but the air pushes back. And then there is the third force, and this one is subtle. It is called ambipolar diffusion. Ambipolar diffusion sounds complicated, but the idea is actually kind of simple. Remember how the magnetic field lines grab onto charged particles? Well, only about 1 in every 10 million particles in a molecular cloud is charged. The rest are neutral. They are just regular, uncharged hydrogen and helium atoms. So while the charged particles are stuck to the magnetic field lines, the neutral particles can slip right past them. They can drift. This process is incredibly slow. It takes millions of years for a neutral atom to drift across the magnetic field lines and join a growing clump of gas. It is like a slow leak in a balloon. The gas is trying to escape the magnetic grip, but it can only do so at a crawl. So you have these three forces: turbulence, magnetic fields, and ambipolar diffusion. And they are all working together, not in harmony, but in a chaotic, tangled dance to hold the cloud up against gravity. Gravity is the bully in this schoolyard. It is the strong, silent force that just wants to pull everything together. But these three forces are the bullies who push back. They create a stalemate, a long, grinding cold war inside the cloud. This is why the known scale is so deceptive. When you look at a picture of the Orion Nebula or the Eagle Nebula, you see something serene. You see beautiful flowing colours and glowing gas. It looks peaceful. It looks like a nursery, a calm, quiet place where stars are born in gentle silence. But the reality is the exact opposite. It is a war zone. Every cubic light year of that cloud is a battleground. Turbulence is smashing gas clouds together at supersonic speeds. Magnetic fields are straining and snapping like rubber bands. And gravity is constantly pulling, trying to get the upper hand. The cloud is not collapsing. It is not exploding. It is just holding itself together by a thread, locked in a slow motion, million-year-long fight for survival. And it is this very stalemate, this fragile balance, that makes star formation possible. If gravity won too easily, everything would collapse into a single supermassive black hole. If turbulence and magnetism won completely, the clouds would just dissipate into nothing, and no stars would ever form. But the balance is just right. The tension is perfect. It allows small pockets of gas in the densest filaments, at the most chaotic intersections, to slowly, over millions of years, overcome the resistance. They squeeze through the magnetic field lines, they ignore the turbulence, and they begin to collapse. It is a slow victory, a grinding, bitter war of attrition, but gravity eventually wins small battles, and those small victories are where stars are born. So the nursery is not a cradle, it is a battlefield, and the fight is not over. It is happening right now, all around us, in the dark, cold spaces between the stars. The calm appearance of a nebula hides a violent, ongoing war, and we are just beginning to understand the brutal complexity of that war. The balance is so delicate that it almost seems impossible. For decades, astronomers struggled to model star formation on computers because the numbers simply did not add up. Every time they simulated a giant molecular cloud using the known laws of physics, the cloud would collapse in 100,000 years, forming a single massive star. It would never produce the kind of star clusters we actually see in the real universe. The simulations were wrong, and the reason they were wrong is that they were missing the feedback. They were missing the fact that the stars themselves, once they finally manage to be born, immediately start fighting back. The war does not end when the star ignites. That is just the beginning of the second phase. Consider the Orion Nebula again, that beautiful glowing cloud you can see with your own eyes. The reason it glows is not because of some gentle internal light. It glows because a group of massive stars, called the Trapezium Cluster, are blasting the surrounding gas with ultraviolet radiation so intense that it strips electrons off the hydrogen atoms. When those electrons recombine, they emit that characteristic red and green glow, but that glow is just the visible evidence of a much more violent process. These stars are carving a bubble in the molecular cloud. They are literally blowing the gas away. The radiation pressure from their light, the intense heat of their stellar winds, and the shock waves from their eventual supernova explosions are all pushing against the cloud, shredding it, evaporating it, and destroying the very nursery that gave them birth. And this is not an accident. This is a fundamental part of the regulation of star formation. The universe does not allow stars to form unchecked. As soon as a cluster of stars ignites, it begins to shut down star formation in its immediate vicinity. The radiation and winds clear out the remaining gas, preventing any more stars from forming nearby. This is why star formation is such an inefficient process. On average, only about 1% of the gas in a giant molecular cloud actually ends up in stars. The other 99% is either blown away by the newborn stars or left behind as the cloud dissipates. The cloud is a cradle that is destined to be destroyed by its own children. But the story gets even stranger when we look beyond individual clouds to the scale of entire galaxies. When we observe galaxies like the Milky Way, we see that star formation is not a constant, steady process. It happens in bursts. Galaxies go through periods of intense star formation called starbursts, followed by long periods of relative quiet. Something is driving this cycle. Something larger than a single molecular cloud is at play, and the most likely candidate is the spiral arms themselves. The spiral arms of a galaxy are not solid structures. They are density waves. Think of a traffic jam on a highway. The cars are moving, but the jam itself stays in roughly the same place as new cars enter from behind and old cars exit in front. That is what a spiral arm is. It is a moving wave of density that sweeps through the galactic disk. As a giant molecular cloud drifts into a spiral arm, it gets compressed. The density wave squeezes the cloud, triggering the collapse of its densest filaments. This is why we see more young stars in spiral arms than in the spaces between them. The arms are the star-forming factories of the galaxy, but even this is not a simple process. The compression from the spiral arm can be too much. It can trigger such a violent burst of star formation that the resulting supernovae blow the gas out of the galaxy entirely. This is called a galactic wind. In massive active galaxies, these winds can eject billions of solar masses of gas into intergalactic space, effectively starving the galaxy of the fuel it needs to form future stars. The galaxy can literally choke on its own star formation, and once that gas is gone, it is gone for good. The galaxy becomes a red and dead elliptical, a fossil of its former self. This is the ultimate Cold War of the cosmos. It is not just a battle between gravity and turbulence in a single cloud. It is a battle between galaxies and their own evolution. It is a feedback loop that spans billions of years and billions of light years. The stars that are born today will determine whether their galaxy lives or dies tomorrow. And the universe as a whole is slowly losing this war. The rate of star formation peaked about 10 billion years ago and has been declining ever since. The universe is running out of gas. The molecular clouds are being consumed faster than they can be replenished. The cosmic nursery is slowly emptying out, and we are living in the twilight of star formation. One day, perhaps 100 trillion years from now, the last star in the universe will flicker out, and the Cold War will finally be over. But until then, the battle rages on in the dark, silent, frigid spaces between the stars. You stand in the cold, vast silence of space, and you think you know the stars. You look up at the night sky and see gentle, twinkling lights. But that is a lie. A comforting, beautiful lie. The stars are not gentle. They are weapons. They are the most violent, unforgiving engines in the universe. And for the last 13 billion years, they have been waging a relentless war against the very clouds that gave them life. This is the Cold War between the stars. And in this chapter, we are going to arm ourselves with the truth. We are going to look at the arsenal of a star. And let me tell you, it is terrifying. Let's start with the most common weapon in a star's arsenal. The quiet one. The one that never sleeps. It is called a stellar wind. Every single star in the universe has one. Our own sun, that big yellow ball of warmth we depend on for everything, is constantly screaming. It is kicking out a stream of charged particles, protons and electrons in every direction, all the time. You cannot see it, but it is there. The solar wind pours off the sun at speeds between 400 and 800 kilometers every second. That is fast enough to cross the entire Atlantic Ocean in the blink of an eye. And it carries a lot of mass. Roughly 1 million tons of material leaves the sun every single second. 1 million tons. Gone. Just thrown away into the void. It sounds enormous, but for the sun it is barely a whisper. The sun is so big that it will keep doing this for billions of years without even noticing. But here is where things get scary. Our sun is a weakling, a runt, a little suburban star. The real monsters, the O-type stars, they are the heavyweight champions of the galaxy. These are stars with masses tens of times greater than our sun, burning so hot that they are blue-white, almost blindingly bright. And their stellar winds? They are not a whisper. They are a cosmic hurricane. An O-type star drives a stellar wind that is 10 billion times more powerful than the wind from our sun. Let that sink in for a second. 10 billion. That is not a typo. These stars are blowing off material at millions of tons per second, with speeds that can exceed 2,000 kilometers a second. They are essentially bleeding energy into the space around them. And what happens when you have a wind that's strong blowing into the cold, dense gas of a giant molecular cloud? You get a bubble. A wind-blown bubble. The star sits in the center, and its wind pushes outward, shoving the surrounding gas away, carving out a cavity of hot, thin plasma. These bubbles are huge. They can stretch for dozens of light years across. But the real show starts when you stop looking at just one star, because massive stars do not like to be alone. They are born in clusters, in giant stellar nurseries. So you get a whole bunch of these O-type monsters, all firing their winds off at the same time. The individual bubbles merge. They combine, and you get a superbubble. Take the Cygnus superbubble, for example. It is a massive structure in the constellation Cygnus, and it spans roughly 500 light years across. 500 light years, think about that. Light itself, travelling at 300,000 kilometers every second, takes 500 years to go from one side to the other. That bubble was carved out by the combined winds of dozens of massive stars, and as it expands, it sweeps up all the interstellar gas and dust, pushing it into a dense shell around the outside of the bubble. It is like a snowplow, pushing all the material to the edges. And that shell, that compressed wall of gas, that is where new stars are born. The pressure squeezes the gas until it collapses under its own gravity, and you get a new generation of stars lighting up right on the edge of the destruction. The weapons of the old stars create the nurseries for the new ones. It is a brutal, beautiful cycle. But stellar winds are just the opening salvo, that is the pea shooter. The real nuclear option, the one that truly shakes the galaxy, is the supernova. When a massive star runs out of fuel, its core collapses, and it explodes with a fury that is almost impossible to comprehend. A single supernova releases something like 10 to the 44th joules of energy. That is a 1 followed by 44 zeros. It is more energy than our sun will produce in its entire 10 billion year lifetime, all released in a matter of seconds. The shockwave from that explosion expands outward at incredible speeds, anywhere from 10,000 to 30,000 kilometers per second. At those speeds, you can cross the entire solar system in a few hours. One of the most famous examples is Cassiopeia A. This is a supernova remnant, the expanding shell of debris from a star that exploded right here in our own Milky Way. We think the light from that explosion first reached Earth around the year 1680. It would have been visible to astronomers at the time, though strangely, no definitive historical records of it exist. But the remnant is still there, still expanding, still glowing in radio and X-ray wavelengths. The shock wave from Cassiopeia A is still ploughing through the interstellar medium, and it teaches us a lot about how these explosions work. As the shock wave expands, it enters what we call the Sedov-Taylor phase. This is a mathematical model that describes how the blast wave decelerates over time. In the very beginning, the explosion is so energetic that it just ploughs through everything like a hot knife through butter. But as it sweeps up more and more interstellar gas, it starts to slow down. The energy gets diluted. The shock front cools, but it is still moving fast enough to compress and heat the gas it encounters. It is still driving material outward, still doing work. And it is during this phase that things get really interesting, because space is not a smooth, uniform place. It is lumpy. It is clumpy. You have dense pockets of gas and dust. You have filaments. You have clouds of all different sizes. When the supernova shockwave hits these lumps, you get instabilities. Specifically, you get Rayleigh-Taylor instabilities. This is a fancy physics term for a very simple concept. Imagine you have a dense fluid sitting on top of a lighter fluid. The interface between them is unstable. It wobbles. It shreds. It forms these beautiful, chaotic fingers of material. When a supernova shockwave hits a dense cloud of gas, the interface between the shock and the cloud becomes unstable. The cloud starts to shred. The hot, fast-moving gas from the explosion rips into the cold, dense gas of the cloud, tearing it apart. But here is the kicker. As it shreds the cloud, it also compresses certain pockets of gas. The instabilities create these tiny dense knots that get squeezed even tighter. And sometimes, just sometimes, those knots get squeezed enough to trigger gravitational collapse. A supernova can destroy a cloud, but it can also plant the seeds of new stars within that same destruction. The weapon is both a destroyer and a creator. Look at the Vela supernova remnant. This is a massive, spectacular structure in the southern sky, the relic of a star that exploded about 11,000 years ago. 11,000 years is a long time for us, but in cosmic terms, it is the blink of an eye. And the Vela remnant is still interacting with the surrounding material from the giant molecular cloud it was born in. The shockwave is still ploughing through that gas, still compressing it, still triggering star formation. You can see the filaments of glowing gas, the wisps of cosmic debris, the evidence of the explosion still reverberating through the interstellar medium. The Cold War is not a quick battle. It takes tens of thousands of years for a single supernova to finish its work. And then there is the payload. The supernova is not just a blast of energy, it is a factory, a recycling plant. Inside the core of that massive star, nuclear fusion was building heavier and heavier elements. When the star explodes, it scatters those elements across the galaxy. A single supernova can return about 10 to 15 solar masses of material back into the interstellar medium. That material is not just hydrogen and helium. It is oxygen. It is carbon. It is silicon. It is iron. All the building blocks of planets. All the building blocks of life. Every atom of oxygen in your lungs. Every atom of carbon in your body. Every atom of iron in your blood was forged in the heart of a massive star and scattered across space by a supernova. The weapons of stellar warfare are the very reason you exist. But the violence does not stop with the blast wave. Supernovae are also the source something else. Something invisible. Something that can travel through solid matter like it is not even there. I am talking about cosmic rays. These are extremely high-energy particles, mostly protons and atomic nuclei, that are accelerated to near the speed of light by the shock waves of supernovae. They are the shrapnel of the explosion, and they can travel enormous distances, penetrating deep into the hearts of molecular clouds. Cosmic rays can ionize the gas inside these clouds, stripping electrons from atoms, and that ionization changes the chemistry of the cloud completely. It heats the gas, It drives chemical reactions. It can even influence how the cloud collapses to form stars. The supernova reaches out and touches the future from millions of years away. And we cannot forget the smallest weapons in the stellar arsenal, the ones that come from the youngest stars. Before a star even gets big enough to explode, it is already causing trouble. When a newborn star is still forming, it is surrounded by a spinning disk of gas and dust. That disk feeds material onto the star, but it does not all fall in. Some of it gets funneled by the star's magnetic field and launched outward in twin, high-speed jets. These are called protostellar jets, or Herbig-Haro objects when they light up from the shock of hitting surrounding gas. And these jets are not gentle. They can shoot out at speeds between 100 and 300 kilometers per second. They carve tunnels through the molecular cloud, ploughing through the gas and creating cavities that can stretch for light years. A beautiful example is HH211, found in the Perseus molecular cloud. This is a young star, still buried in its cocoon, launching a spectacular bipolar jet. You can see the two beams of glowing gas, one pointing this way, one pointing that way, as the jet slams into the surrounding material. And sometimes the star does not just shoot the jet straight out, it wobbles. The axis of rotation of the star and its disk can precess, like a spinning top that is wobbling. When that happens, the jet carves a corkscrew pattern into the cloud. It is a beautiful, almost artistic structure, but it is also a weapon. It punches holes in the cloud, releasing pressure, stirring up the gas, and preventing the whole thing from collapsing too fast. Even the babies are fighting. So when you put it all together, the picture is clear. Stellar winds, from gentle breezes to cosmic hurricanes, carve bubbles and superbubbles. Supernovae, the nuclear option, release unimaginable energy, shredding clouds, triggering star formation, and seeding the galaxy with heavy elements. Cosmic rays, the invisible shrapnel, penetrate deep into the darkness, changing the chemistry of the future. And protostellar jets, the weapons of the newborns, punch holes and stir the pot. This is the feedback loop. The stars are born from the clouds. They live, they fight, they destroy. And from their destruction, new stars are born. It is a cycle that has been running for 13 billion years. And it is still running right now, all around us. We live in the middle of it. We are the product of it. Every time you look up at the night sky, you are seeing the battlefields. The Cold War between the stars is not a metaphor. It is the fundamental engine of the galaxy. It is the reason we are here, and it will continue until the very last star flickers out 100 trillion years from now. The weapons are still firing. The war is still raging. And we are just beginning to understand the true scale of the arsenal. So the galaxy is a battlefield, and we have named the weapons: stellar winds, supernovae, cosmic rays, protostellar jets. But a soldier does not just fire a gun into the void. They aim. They have a target. And the primary target of all this stellar violence, the thing that receives the brunt of the bombardment, is the giant molecular cloud. These are the vast, cold, dark structures that drift through the galactic disk. They are made mostly of molecular hydrogen, but they are laced with dust and a complex cocktail of other molecules. They are the only places in the galaxy where stars can form, and they are under constant attack. The most massive of these clouds, the truly colossal ones like W49A or the W51 complex, can have masses of over 1 million solar masses. They span hundreds of light years across. They are the cathedrals of the galaxy, the quiet sanctuaries where the next generation of stars is conceived. But they are not peaceful. They are turbulent. They are chaotic. And the reason for that turbulence, the reason they do not just collapse into a single supermassive star, is the feedback from the very stars they create. It is a beautiful, violent paradox. A cloud gives birth to stars, and those stars immediately begin to tear the cloud apart. The cloud fights back, of course. Its own gravity is a powerful force, pulling everything inward. But the stars have the advantage of energy. They are the ones with the firepower. Let us look deeper at the blast wave. When a supernova goes off inside or near a giant molecular cloud, the initial shock is impossibly hot. Temperatures can reach millions of degrees. The shock front is a thin, nearly discontinuous layer, where the properties of the gas change dramatically. Ahead of the shock, you have cold, dense molecular gas, maybe 10 degrees above absolute zero. Behind the shock, you have a plasma that is 1,000,000 degrees. The density drops by a factor of about 4 across the shock front itself, but the temperature jump is what matters. That extreme heat creates enormous pressure. The shock expands outward, and as it does, it sweeps up more and more of the cold gas. This swept-up gas piles up behind the shock, creating a dense shell. Now, this shell is not stable. It is thin, it is dense, and it is being pushed from the inside by the hot, tenuous gas of the supernova remnant. This configuration is a perfect recipe for the Rayleigh-Taylor instability we mentioned earlier. The dense shell is being accelerated outward by the lighter gas behind it. It is like a heavy blanket being lifted by a cushion of air. The interface between the two will inevitably ripple. Fingers of dense gas will push outward, and bubbles of hot gas will push inward. These instabilities can grow and fragment the shell, creating clumps and filaments. But they also do something else. They can create the conditions for new star formation. The dense fingers, squeezed from all sides, can become gravitationally unstable. They can collapse, and so a supernova, which seems like the ultimate act of destruction, can actually trigger the birth of new stars in the shell of debris it creates. But the supernova does not work alone. Remember the stellar winds. Before the star even exploded, it was blowing a powerful wind for millions of years. That wind carved out a low-density bubble around the star. When the star finally goes supernova, the blast wave expands rapidly through this pre-cleared cavity. It does not have to plough through dense gas immediately. It can expand almost freely at very high speed for a long time. This means the supernova remnant can grow much larger and live much longer than it would if the star had been sitting in a dense cloud. The wind prepares the battlefield for the explosion. It is a coordinated assault. And then there is the context of the galaxy itself. The Cold War between the stars is not fought in isolation. It is shaped by the grand structure of the Milky Way. Our galaxy is a spiral, with elegant arms winding out from the centre. For decades, astronomers wondered why these spiral arms were so prominent. Why do they have so many bright young stars? The answer lies in the interplay between the stars and the clouds. The spiral arms are density waves. They are not physical objects, but rather patterns of gravitational compression that move through the galactic disk. As a giant molecular cloud drifts into a spiral arm, it feels a gravitational squeeze. This compression can trigger the cloud to begin collapsing, forming clusters of stars. Those clusters, especially the massive stars, then begin their work. Their stellar winds and supernovae carve out the bubbles and superbubbles that delineate the edges of the spiral arms. The stars light up the arms, but the shock waves from their deaths also help to shape them. The stars are not just inhabitants of the galaxy. They are architects, they are sculptors. We can see this process happening in real time all across the sky. One of the best examples is the Rosette Nebula. This is a gorgeous, flower-shaped emission nebula in the constellation Monoceros. At its centre lies a cluster of hot massive stars known as NGC 2244. Those stars are blasting out an intense stellar wind, and together they have carved a large cavity in the centre of the molecular cloud that gave them birth. The nebula itself is the glowing, ionized rim of that cavity. Look closer at the rosette, and you will see pillars of dense gas, dark silhouettes against the bright background. These are the same kind of pillars you see in the famous Pillars of Creation in the Eagle Nebula. They are dense fingers of gas that are being eroded by the radiation and winds from the central stars. And at the tips of these pillars, new stars are forming. The very same forces that are destroying the cloud are also compressing its last remnants into new suns. And this leads us to a sobering thought. The Cold War between the stars is a war of exhaustion. The clouds have a finite amount of gas. Every time a generation of stars is born, they consume some of that gas to fuel their fusion. Every time a massive star dies in a supernova, it blasts a significant fraction of that gas out of the cloud entirely, sometimes right out of the galaxy itself. This is called galactic feedback. and it is a crucial process in the evolution of galaxies. If stars did not blow away the gas, galaxies would turn all their gas into stars very quickly, and the universe would be a much more boring place. But the feedback slows down the star formation rate. It regulates it. It allows galaxies to live for billions of years, slowly converting their gas into stars. There is a famous calculation. In the Milky Way, there is enough molecular gas to form stars at the current rate for about another 1 to 2 billion years. But that is not the whole story. That gas is being constantly enriched by the heavy elements from supernovae. It is being heated and stirred by stellar feedback. It is being replenished to some extent by gas falling in from intergalactic space. The Cold War is not a closed system. The galaxy is connected to the larger cosmos, the supernovae that happen in the disk blow bubbles that can vent hot gas into the galactic halo. That gas can cool, fall back down, and seed new clouds. It is a grand cycle, a cosmic fountain powered by the violence of the stars. So let us return to the beginning, to that cold vast silence. You stand on a planet, looking up at the night sky. You see the stars as points of light, but now you know the truth. Each one of those points is a potential weapon. Each one is engaged in a relentless struggle with the darkness that surrounds it. Some are raging hurricanes. Some are ticking bombs. Some are barely flickering embers. But they are all part of the same war. The Cold War between the stars is the creative destruction that builds the universe. It is the furnace that forges the elements. It is the engine of change. And it will continue, long after our planet is gone, long after our sun has become a quiet white dwarf, long after the last star in the Milky Way has blinked out. The weapons will fall silent. The clouds will disperse. The war will end. But for now, in this moment of cosmic time, the battle rages on, and we are fortunate enough to witness it. But even as we imagine the end, the final fading of the last ember, the quiet settling of an eternal darkness, we must remember that this war is not fought only with fire and gravity. It is fought at a level so small, so intimate, that we could never see it with our own eyes. It is a war of atoms, of molecules, of the very stuff that makes up everything we touch, everything we breathe, everything we are. And this chemical dimension of the struggle is, in many ways, the most important front of all, because while stars may collapse and galaxies may drift apart, it is this invisible battle, waged in the frozen voids between suns, that decides whether any world can ever be called home. So let us shrink ourselves down. Let us imagine that we are not human beings, not even grains of dust, but something far smaller, a single atom floating alone in the vastness of interstellar space. At 10 degrees above absolute zero, you are cold beyond anything Earth can offer. Colder than the darkest night on Pluto, colder than the shadowed craters of the Moon. At this temperature, molecules barely move. They drift, they collide, but they do so with a sluggishness that would make a glacier seem frantic. And yet, out of this frozen silence, chemistry happens. Not the kind of chemistry you remember from high school labs, with bubbling beakers and colourful flames, but something far more subtle, far more patient. Ion-molecule reactions, they call them, and these reactions are the backbone of the entire chemical war. You see, at 10 Kelvin, most molecules are neutral. They do not carry a charge. They just sit there, content to be cold and still, but every once in a while, a high-energy particle, a cosmic ray or a stray photon, slams into one of these molecules and knocks an electron loose. Suddenly, that molecule becomes an ion. It has a positive charge. And in the vacuum of space, where everything is neutral and lonely, a charged particle is like a magnet. It attracts. It reacts. It becomes the spark that ignites a chain. And the most important of these sparks is the trihydrogen cation, H3+. It is in its simplest form just 3 hydrogen atoms with an extra positive charge. It sounds almost ridiculous, does it not? So simple, so small. And yet without it, the universe would be chemically sterile. H3+ is the key that unlocks the door to complexity. It is the catalyst, the initiator, the first domino that sets off a cascade of reactions. When it forms, it immediately starts reacting with everything it meets. With carbon monoxide, with water, with methanol, with any molecule unfortunate enough to drift into its path. and each reaction produces something new, something larger, something more interesting. A chain of carbon here, a nitrogen bond there. Step by step, molecule by molecule, the universe builds itself from scratch. But where do these molecules come from in the first place? The answer, as it so often is dust. Not the dust under your bed, but the dust of space. Tiny grains of silicate and carbon, no bigger than a speck of smoke, that drift through the void. And on the surface of these grains, something remarkable happens. In the cold, dark regions between stars, molecules like water, methanol, and carbon monoxide freeze out onto the grains, forming thin layers of ice. A water ice mantle, they call it. Think of it like frost on a window pane, but on a grain so small that you could fit 1 billion of them on the head of a pin. And within that frost, chemistry is waiting. Because out here, in interstellar space, nothing is safe for long. Ultraviolet photons from nearby stars, or from the distant glow of the galaxy itself, can penetrate these clouds. They hit the ice mantles. They crack the molecules apart. They generate radical species, fragments of molecules with unpaired electrons. And radicals, like ions, are hungry. They want to react. They want to bond. They want to become whole again. So they drift across the surface of the dust grain, searching for a partner. And when they find one, they recombine into something new, something complex, something that could never have formed in the gas phase alone. This is where the magic happens. This is where simple things become complicated things, where methanol becomes formaldehyde, where formaldehyde becomes sugars, where sugars, perhaps, become the building blocks of life. And we know this is real because we have seen the evidence. In the Sagittarius B2 cloud, a giant molecular cloud near the centre of the Milky Way, astronomers have detected the precursors of glycine. Glycine, the simplest amino acid, the stuff of proteins, the stuff of you and me. We are talking about the raw ingredients of biology, cooking in a molecular cloud 26,000 light-years away. It is not a stretch to say that the origin of life on Earth may trace directly back to these interstellar reactions. That the molecules that eventually assembled into the first living cell were born not in some primordial soup, but in the frozen darkness between the stars, and when comets form, they gather up this chemical heritage. They sweep through the cloud, accreting dust and ice and organic molecules, carrying them along for the ride. For billions of years, comets orbit the sun, delivering their cargo to planets, to moons, to any world unlucky enough to cross their path. And on those worlds, the chemistry continues. The water that fills your glass, the carbon in your bones, the nitrogen in the air you breathe, all of it, every single atom, was once part of an interstellar cloud. You are made of star stuff, yes, but more than that, you are made of cloud stuff. You are the product of a chemical war fought over millions of years in the cold, silent dark. But this war is not only about building molecules, it is also about temperature, because chemistry is deeply sensitive to heat. Too hot and molecules break apart, too cold and they freeze solid. And in the interstellar war, temperature is a weapon used by both sides. On one side you have the sources of heat, ultraviolet radiation from massive stars, cosmic rays from supernovae, turbulence from colliding gas flows, gravitational contraction from collapsing cores. All of these dump energy into the cloud, raising its temperature, stirring up the gas, trying to break the chemical bonds that have taken so long to form. It is a ceaseless assault, a bombardment of energy that would, under normal circumstances, turn any organic molecule into a pile of ash. But the cloud fights back. It has its own cooling mechanisms. Carbon monoxide, for example, is an excellent coolant. When it collides with other molecules, it releases energy in the form of light, radiation that can escape into space. This is the cloud's way of saying, I am too hot, I need to cool down. And it does this constantly, pouring energy out into the void, keeping itself stable. Dust grains, too, play a role. They absorb radiation and re-emit it at longer wavelengths, carrying heat away from the inner regions of the cloud. And molecular hydrogen, the most abundant molecule in the universe, helps as well, though it is not as efficient. It is a slow process, this cooling, but it is relentless. And at the boundaries of these clouds, where ultraviolet light from nearby stars begins to penetrate, you find the true front lines of the temperature war. These are the photodissociation regions, the PDRs. They are the thin interfaces where the heat of the star meets the cold of the cloud, where photons rip molecules apart, where chemistry is simultaneously destroyed and created. The Horsehead Nebula, that iconic silhouette rising from a sea of glowing gas, is a perfect example of a photodissociation region. The dark shape of the horse's head is actually a dense clump of molecular gas, shielded from the radiation by its own weight. But around its edges where the light hits, the chemistry is fierce. Molecules are broken, atoms are freed, new reactions begin. It is a battlefield, painted in light and shadow, and it is beautiful. But there is another weapon in this war, one that we can actually see. Masers, and no, not lasers. Masers are the microwave equivalent. They amplify radiation at specific frequencies, producing beams of intense, coherent light. Only it is not visible light, it is radio light, invisible to our eyes, but perfectly clear to our telescopes. And masers are everywhere in the universe, shining like beacons in the dark. Water masers, for instance. The most famous of these is W49N, a region of intense emission in the constellation Aquila. Here, water molecules are pumped by radiation from a young, massive star, emitting at a frequency of 22 GHz. The signal is so strong that we can track it across the galaxy. Methanol masers are even more common. They form in the dense, collapsing cores where new stars are being born. They are the unambiguous signposts of high-mass star formation, a chemical signal that says right here, a star is being built. And OH masers, hydroxyl radicals, they appear in the expanding shells of dying stars, marking the final stages of a stellar life. And then there are SiO masers from silicon monoxide, which trace the atmospheres of evolved stars, the red giants and supergiants that are about to blow off their outer layers into space. These masers are not just curiosities, they are tools. Imagine trying to map the rotation of the entire Milky Way galaxy. How do you do it? You cannot see the spiral arms directly. They are hidden behind thick clouds of dust. But masers shine through. They are bright, they are narrow, and they are locked to the motion of the gas around them. So astronomers launched the Bessel survey, the Bar and Spiral Structure Legacy survey. They used methanol masers to trace the positions and velocities of star-forming regions across the galaxy, and from that data they built a map of the Milky Way's rotation curve, the speed at which different parts of the galaxy orbit the centre. It is a masterpiece of indirect observation, a way of seeing the invisible by listening to the whispers of molecules, and sometimes those whispers become shouts. Maser flares, sudden, dramatic increases in brightness that last for weeks or months. What causes them? Protostellar accretion bursts. When a young star is in the process of forming, it does not simply light up like a light bulb. It grows by pulling in material from a surrounding disk, and sometimes the disk becomes unstable. A clump of gas and dust falls in all at once. The star heats up, and the masers, sensitive as they are to the energy around them, flare in response. It is a signal, a chemical scream that says something is happening here, something violent, something new. So you see, this war is not just about destruction, it is about creation. It is about the beautiful, chaotic, almost incomprehensible process by which the universe takes simple elements and builds them into complex molecules, into water, into amino acids, into the very stuff of life. The temperature war, the chemical war, the molecular struggle, it is all connected. And it is all happening right now, in clouds that span hundreds of light years, in dust grains smaller than a whisper, in maser beacons that cross the galaxy in an instant. We are witnesses to this war. We are not observers separated by time and space. We are participants, because the atoms in your body were once part of these clouds. The carbon in your DNA was once locked in a water ice mantle on a dust grain. The oxygen you breathe was once a radical, searching for a partner in the dark. And somewhere out there, in a collapsing core near the centre of the galaxy, a new star is being born. Its heat will destroy some molecules and create others. Its masers will flare, its chemistry will begin, and if the universe is lucky, if the war goes well, that star will one day have planets, and those planets will have water, and that waters will have the molecules that, given enough time, enough patience, enough cold and heat and radiation, will become life. The war rages on. The clouds disperse. The weapons are chemistry and temperature, time and chance, and we are here on this fragile world because of it, because of a war fought in the emptiness between the stars, a war that began long before the Earth existed, and will continue long after it is gone. A war that, if we look closely enough, tells us where we came from, and maybe, just maybe, where we are going, and so the war does not end. It cannot, for the universe is a restless engine, and its chemistry is never finished. Even as a cloud begins to break apart, scattered by the first light of a newborn star, even as its molecules are torn asunder by ultraviolet radiation, new battles begin elsewhere. The debris of one molecular cloud becomes the raw material for another. The atoms that were once part of a grand, cold structure drift for millions of years through the void, only to be gathered again by gravity into a new assembly. This is the cycle. This is the relentless, eternal churn of galactic chemistry. Consider the life of a single carbon atom. It is forged in the heart of a star, in the final stages of nuclear fusion, when helium burns into carbon. That star, perhaps a red giant, then expels its outer layers in a gentle wind, and the carbon atom is cast out into space. It drifts alone for eons. Eventually it finds its way into a molecular cloud. It lands on a dust grain. It becomes part of a water ice mantle. It reacts with hydrogen, with oxygen, with nitrogen. It becomes part of a complex organic molecule. That molecule, perhaps methanol, is incorporated into a comet. The comet falls toward a young star, and the carbon atom is released into a planetary atmosphere. It falls into an ocean. It becomes part of a living cell. It is breathed, eaten, broken down, built up again. It becomes part of a tree, then part of a leaf, then part of the soil. It is released into the air, captured by another plant, passed along the food chain. Eventually, it is buried, compressed, turned into coal or oil. It is burned, released again, and the cycle continues. The carbon atom has no memory of its journey. It simply is. But we who can trace that journey, we can see the war. And at the heart of this war there is a profound asymmetry. The universe is built on a knife's edge between order and chaos. Chemistry is the force that builds order, molecules, chains, rings, structures of staggering complexity. But thermodynamics, the great leveller, seeks to tear it all down. The second law of thermodynamics states that entropy, disorder, must always increase. So how, then, can a molecular cloud, a region of space so cold and seemingly dead, produce the building blocks of life? How can order emerge from chaos? The answer lies in the flow of energy. The molecular cloud is not a closed system. It is open to the universe. Energy pours in from stars, from cosmic rays, from the gravitational collapse of the cloud itself. And that energy, as it flows through the system, can drive local decreases in entropy. It can create order. It can build molecules. It is like a whirlpool in a stream, a temporary beautiful structure that exists only because of the flow of water around it. The cloud is the same. It is a temporary ordering of atoms, sustained by the energy that flows through it. This is the deep philosophical heart of the chemical war. It is not a conflict between good and evil. It is a conflict between the tendency of the universe to become simple, uniform, and dead, and the tendency of matter, when driven by energy, to become complex, diverse, and alive. And the battlefield is not just in the stars. It is in you. Every second of your existence, your body is waging this war. Your cells are burning molecules for energy, creating order within themselves while dumping entropy into the environment. You are a local rebellion against the cosmic tendency toward decay, and the tools you use, the enzymes, the proteins, the DNA, are all the products of that ancient interstellar war. And there is a final haunting aspect to this war. It is the question of rarity. How common are these chemical processes in the universe? We know that molecular clouds are everywhere. We know that the reactions we have described are universal. The laws of physics and chemistry are the same everywhere. So the building blocks of life should be common. But is life itself common? We do not know. The chemical war can produce amino acids, sugars, lipids, even the precursors of RNA. But crossing the gap from complex chemistry to a self-replicating evolving system, that is a different war altogether. It is a war that we do not yet understand. It may be that this final step is so difficult, so improbable, that it has only happened once in the entire observable universe. Or it may be that it happens all the time, on countless worlds, in countless systems, and the universe is teeming with life, hidden from us by the vast distances between the stars. The James Webb Space Telescope, now peering into the infrared universe, is our newest weapon in this war of understanding. It can see through the dust that hides the birthplaces of stars and planets. It can detect the spectral fingerprints of molecules that were previously invisible. It can analyze the atmospheres of exoplanets, searching for signs of biological activity. Every new observation is a reconnaissance mission into the chemical battlefield of the cosmos, and every new result reshapes our understanding of the war. Consider the Orion Nebula, that great stellar nursery visible to the naked eye as a fuzzy star in the sword of the constellation. The Webb telescope has turned its gaze upon it and found something astonishing. Within the protoplanetary disks surrounding young stars, it has detected methylcation, a molecule that plays a key role in building more complex carbon-based chemistry. This is not just a confirmation of a theory. It is a direct observation of the chemical chain reaction that we have been describing, happening in real time around a star very much like the Sun was 4.5 billion years ago. It is as if we are watching the opening moves of the very war that led to our own existence. And this brings us to the most intimate battlefield of all. The Earth itself. Our planet was not formed in isolation. It was built from the debris of a molecular cloud, from the dust and gas that swirled around the young Sun. And it was bombarded continuously by comets and asteroids that carried the chemical harvest of interstellar space. The water in our oceans, the carbon in our bodies, the nitrogen in our atmosphere, all of it was delivered by these celestial messengers. The chemical war did not stop when the Earth formed. It simply changed its venue. On the early Earth, the same reactions that had occurred on dust grains in space now occurred in shallow ponds, in hydrothermal vents, in the atmosphere energized by lightning. And eventually, after millions of years of trial and error, the first self-replicating molecule emerged. The war had produced a new kind of soldier, a soldier that could carry the chemical information forward, that could adapt, that could evolve. And now, billions of years later, that war has produced us. We are the descendants of those first replicators. We are the chemical complexity of the universe made conscious. And we have the unique ability to look back at our origins, to peer into the molecular clouds, to listen to the mazes, to trace the reactions that made us possible. We are the universe's way of understanding itself, and the war that we see, the war of ice and dust and radiation, is not a remote spectacle. It is our own history, written in the language of molecules. So as you sit here, listening to these words, remember that you are a temporary victory in a war that has been raging for 13.8 billion years. The atoms in your body have survived supernovae, travelled across galaxies, nestled in the cold of interstellar space, and participated in reactions that built the very fabric of life. You are a monument to the chemical war. And the war is not over. It continues in every breath you take, in every meal you eat, in every thought that crosses your mind. The cloud that made you is gone, but the war that it fought is still being fought everywhere, in the void between the stars. And we are the witnesses. We are the evidence. We are the living proof that the cold, the dark, and the silence can, given enough time and enough energy, produce something that can look back and understand. We have looked at the quiet places, the cold places, the places where the universe seems to be sleeping. But the Milky Way is not asleep. It is not a peaceful, static painting on the dome of the sky. It is a battlefield, a war zone. And the battlegrounds we are about to explore are not the size of a city or a continent or even a planet. They are thousands of light years across. They are entire regions of space where the forces of creation and destruction are locked in a struggle so violent, so immense, that it reshapes the very structure of our galaxy. We are going to zoom out now, way out, and look at the biggest arenas in this Cold War between stars. But first, let us take a moment to understand the scale of the army. The Milky Way is not just a collection of 200 billion stars that sit there peacefully minding their own business, burning hydrogen. No. The galactic battlefield is defined by its geography, and the most critical terrain in this war is the gas. If stars are the soldiers, then the giant molecular clouds are the supply depots, the barracks, the factories where these soldiers are born. And we do not have a handful of them. We have thousands. The current census of our galaxy that we have managed to piece together, using radio telescopes and infrared surveys, which are the only way to see through the dust that hides these nurseries, has identified over 6,000 distinct giant molecular clouds. 6,000. Think about that number. Each one of these things is a reservoir of hydrogen and helium and dust that is hundreds of light years across. Each one contains enough raw material to form tens of thousands of stars. But these clouds are not scattered randomly like confetti. They are organized. They follow a pattern that is dictated by the galaxy itself. Most of these clouds are found in a vast ring that encircles the galactic center. We call it the molecular ring. But do not let the name fool you into thinking it is a pretty little jewel. This ring is a monstrous, chaotic, turbulent annulus of gas that stretches from about 10,000 light-years out from the centre to roughly 15,000 light-years out. It is the primary factory floor of the Milky Way. It is where most of the star formation in our galaxy is taking place right now, at this very second. And it is a veritable shooting gallery. The density of gas in this ring is so high, and the gravitational forces so complex, that clouds are constantly colliding, compressing, and triggering collapse. It is not a calm ring. It is a carousel of destruction that keeps birthing new soldiers to replace the ones that are dying. And then there is the bullseye, the heart of the battlefield. If you travel all the way in towards the centre of the galaxy, past that incredible ring, you enter the central molecular zone. This is a region that surrounds the supermassive black hole at the core of our galaxy, a black hole we call Sagittarius A star. The central molecular zone is unique. The gas there is not like the gas in the spiral arms. It is hotter, denser, and far more turbulent. The pressures are immense. The radiation fields are brutal. This is a place where the war is fought at a fever pitch, and within this zone there is one particular giant molecular cloud that stands out as the crown jewel of the galactic battlefield. Its name is Sagittarius B2. Sagittarius B2 is more than just a cloud. It is a titan. It contains about 3 million times the mass of our Sun, all crammed into a region of space that is only about 150 light-years across. 3 million solar masses. This single object contains enough hydrogen to make 3 million stars just like our Sun. It is the largest giant molecular cloud in the entire galactic centre. And it is not just big, it is incredibly complex. When we look at Sagittarius B2 with our radio telescopes, we do not just see simple hydrogen gas. We see the fingerprints of chemistry. We see complex organic molecules. We see things like ethyl alcohol, the stuff that is in beer and vodka. We see glycolaldehyde, which is a simple sugar. We see amino acid precursors, the building blocks of proteins, the very chemical chains that are essential to life as we know it. This is a staggering fact. Out there, in a region of space that is being blasted by high-energy radiation from a supermassive black hole and thousands of massive stars, nature is building the raw ingredients for life. It is not alive yet, not in any way we could recognize. But the pieces are there. The carbon, the hydrogen, the oxygen, the nitrogen are being assembled into larger and larger structures. Sagittarius B2 is a chemical factory of staggering proportions. It is a place where the universe is practicing for biology, and it is doing so in the middle of the most extreme environment in the galaxy. But the star of the show, quite literally, is the thing at the very centre, Sagittarius A star. This black hole is 4 million times the mass of our Sun. It is a gravitational monster that rules the entire central region of the Milky Way. And it is not a passive observer. It influences the star formation across the entire central molecular zone. The gravitational tides from this black hole are powerful enough to rip giant molecular clouds apart, or compress them into clumps that collapse into stars. The black hole sporadically feeds on gas and stars that wander too close, and when it does, it releases immense flares of X-rays and gamma rays that sweep through the region, heating the gas, stripping electrons from atoms, and altering the chemistry of the clouds. Sagittarius A star is the general of the dark army in the centre of the galaxy. Its influence reaches out across thousands of light years, and its temper tantrums shape the destiny of billions of stars. And there is direct, visible evidence of its temper. Have you ever seen an image of the Milky Way in gamma rays? If you have probably noticed two enormous glowing lobes that extend above and below the disk of the galaxy, like a pair of giant ghostly wings. These are the Fermi bubbles. They were discovered by the Fermi Gamma Ray Space Telescope just over a decade ago, and they immediately rewrote our understanding of the galactic centre. These are not small features. They rise 25,000 light-years above the galactic plane. The entire disk of our galaxy is about 100,000 light-years across. These bubbles are half that size. They are enormous, and they are filled with incredibly high-energy particles, cosmic rays that are emitting gamma rays as they interact with gas and light. The big question is, what created them? We have two leading theories, and both of them are violent. The first theory is that the Fermi bubbles are the fossil remnant of a massive burst of star formation that happened in the galactic centre about 6 to 9 million years ago. Imagine 1,000, 10,000, maybe even 100,000 massive stars exploding as supernovae in a relatively short period. All that energy, all those stellar winds, all those explosions would have combined into a single colossal outflow that punched out of the galactic disk, creating these bubbles. The second theory is even more personal. It is that Sagittarius A star itself went on a feeding frenzy. It swallowed a huge amount of material, perhaps a giant molecular cloud or even a star cluster, and in the process it launched a pair of relativistic jets. These jets would have slammed into the surrounding gas and blasted it outwards, carving the bubbles we see today. Either way, the implication is profound. The galaxy is not just a static spiral, it breathes. It erupts. The centre of our galaxy has a pulse, and every few million years it has a massive heart attack that sends a shockwave a quarter of the way across the galaxy. The Fermi bubbles are the scars of that battle. They are the evidence that the Cold War is not always cold. Sometimes it gets very, very hot. Now let us leave the galactic centre and come home. Let us come to our own neighbourhood. Because we do not have to travel 25,000 light-years to see the war in action. It is happening right in our own cosmic backyard. We are talking, of course, about the constellation of Orion. Orion is probably the most recognizable constellation in the winter sky, but what most people see as a set of stars is actually a window into a massive ongoing conflict. Orion is home to the closest region of massive star formation to Earth. It is about 1,350 light-years away, which is practically next door on the galactic scale, and the entire constellation is surrounded by an enormous structure that tells the history of 1,000 battles. It is called the Orion Eridanus superbubble. This is a cavity in the interstellar medium that is over 1,000 light-years across. It is a giant, ragged hole in the gas and dust of our local arm of the galaxy, and it was not created by a single explosion. It was created by successive generations of supernovae, happening one after another, over a period of about 12 million years. Imagine a stellar nursery. A group of massive stars is born. They live fast, they burn hot, and they die young. The most massive ones explode as supernovae, blasting their outer layers into space. Those explosions create shockwaves that sweep up the surrounding gas, compressing it and triggering the birth of new stars. Those new stars grow up, and the most massive ones explode again. This cycle continues, generation after generation, each explosion adding a little more energy to the bubble, until it is 1,000 light-years across. The Orion Eridanus superbubble is the graveyard of a dozen star clusters. It is a monument to the self-destructive nature of massive stars. But there is a piece of this bubble that we can actually see with a small telescope. It is called Barnard's Loop. It is that faint reddish arc of light that curves around the belt and sword of Orion. Barnard's Loop is not a complete shell. It is a partial shell. It is the edge of the superbubble where the shock wave is still interacting with the surrounding cold gas, causing it to glow. It is a fragment of a much larger story. It is like seeing the rim of a crater and knowing that something huge must have made it, but you can only see a small piece of the edge. And within this region, right in the thick of it, there is a relatively recent explosion. About 500 years ago, in the time of Christopher Columbus and the Renaissance, something happened in the Orion Nebula. It is called the BNKL explosion. This was a catastrophic event. A dense core of gas and dust collapsed in a very specific, very violent way. We do not know exactly what triggered it. It could have been a collision between two massive young stars. It could have been a star that swallowed a smaller companion. Whatever it was, it released an enormous amount of kinetic energy. It literally kicked several protostars out of the region at an incredible speed. We have tracked these runaway stars. They are moving at over 100 kilometers per second. That is 220,000 miles per hour. They are fugitives from the crime scene, and they are telling us that 500 years ago, the Orion Nebula experienced a violent paroxysm that ejected stellar infants into the void. But the violence in Orion is not just ancient history. It is happening right now, in front of our eyes. The heart of the Orion Nebula is a small cluster of very young, very massive stars. We call them the trapezium. These four stars are the heavyweights of the neighbourhood. They are thousands of times more luminous than our Sun. They are incredibly hot, and they are flooding the entire nebula with ultraviolet radiation. This radiation is doing two things. It is ionizing the gas, stripping electrons from hydrogen atoms, and making the nebula glow with that characteristic pinkish-red light. But it is also doing something far more destructive. Scattered throughout the Orion Nebula are over 150 protoplanetary disks. We call them proplyds. These are the cocoons of new solar systems. They are disks of gas and dust that are swirling around young stars, the raw material from which planets are made. But the trapezium stars are killing them. The intense ultraviolet radiation is literally boiling them away. We can see it happening. We can see the radiation blasting the gas off the surface of the disks, creating these beautiful cometary tails that point away from the trapezium. It is a process called photoevaporation. The stars that are trying to be born in Orion are having their planetary nurseries dissolved by the very stars that are lighting up the nebula. It is a heartbreaking sight. It is a cosmic tragedy being played out on a scale of hundreds of worlds. The trapezium is creating beauty, but it is also destroying the potential for life. Orion is local. It is our neighbour. But to see the war at its most spectacular, we have to travel further. We need to go to a place where the scale is so large that it dwarfs everything we have talked about so far. We need to go to the Carina Nebula. Carina is about 7,500 light-years away from Earth. That is 5 times further than Orion, but it is 20 times larger. 20 times. This is not a nebula, this is a province. Carina spans over 300 light-years from end to end. It contains more than 14,000 stars, many of them the most massive and most luminous stars in our entire galaxy. It is a powerhouse of stellar creation, on a scale that defies comprehension. The star that has made Carina famous, the star that draws all the attention, is Eta Carinae. Eta Carinae is a binary star system, but one of its members is a monster. It is estimated to be over 100 times the mass of our Sun. It is one of the most massive stars we have ever seen, and it has a terrible temper. In the year 1843, Eta Carinae threw a fit. It underwent a massive eruption, an event that we call the Great Eruption. This eruption expelled an incredible 40 solar masses of material into space. 40 times the mass of our own Sun, just thrown away. It briefly became the second brightest star in the entire night sky, outshining everything except Sirius, even though it was 7,500 light-years away. That is how bright it was. The material it ejected formed two expanding lobes of gas and dust, which we call the homunculus nebula. It is a tiny little blob of a nebula, only a light year across, but it is moving. The gas in the homunculus nebula is expanding at 650 kilometers per second. It is a bullet. It is a shockwave, and it is screaming out into the surrounding nebula. Eta Carinae is a ticking time bomb. It is expected to explode as a supernova, or perhaps even a hypernova at any time, astronomically speaking. It could happen tomorrow. It could happen in 1,000 years. But when it does, it will be the most spectacular event in the history of human civilization. It will outshine the full moon. It will be visible during the day, and it will send a shockwave through Carina that will reshape the entire region. But Carina is not just about Eta Carinae. The entire region is a war zone. Look at a star cluster called Trumpler 14. This cluster is incredibly young, only about 500,000 years old. That is the blink of an eye in cosmic terms. And these young massive stars are already destroying the cloud that gave birth to them. Their intense radiation and powerful stellar winds are carving cavities in the nebula, pushing the gas away and shutting down star formation in the areas they have already swept clean. They are parricides. They are killing their own mother. And then there is the South Pillar region. This is a part of Carina that looks like a giant finger of dust pointing outward into space. At the tips of these pillars, you can see bright knots of gas. These are protostars. They are trying to form. But the pillars are being eroded away by the same radiation that is destroying Trumpler 14. The pillars are evaporating. The protostars at the tips are racing against time. They have to finish collapsing before their nursery is completely vaporized. Some of them will make it. Most of them will not. They will be left as orphaned, failed stars, or they will simply be dispersed back into the general interstellar medium, their potential lost forever. If Carina is a province, then we have one more stop to make. We have to leave the Milky Way entirely. We have to travel to our nearest major galactic neighbour, the Large Magellanic Cloud. It is a dwarf galaxy that orbits our own, and it is about 160,000 light-years away. And in that little satellite galaxy, there is a nebula that is the most extreme star-forming region in our entire galactic neighbourhood. It is called 30 Doridus, but everyone knows it by its more poetic name. The Tarantula Nebula. If you think Carina is big, the Tarantula makes it look like a backyard fire pit. The Tarantula Nebula is the largest, brightest, most violent star-forming region in the entire local group of galaxies. It is 4 times larger than Carina in terms of the area of glowing gas, and it contains stars that are simply not possible in our own galaxy anymore. At the very heart of the Tarantula is a star cluster called RMC 136A, and within that cluster there is a star, R13601, that breaks the rules. This star is estimated to have a mass of over 200 times that of our Sun. 200 solar masses. The theoretical upper limit for stars in our galaxy was thought to be around 150 solar masses. This thing spits in the face of theory. It is so massive, so incredibly luminous, that it shines with the power of 8 million suns. 8 million. If you put this star at the centre of our solar system, it would vaporize Earth from orbit. It would boil the oceans of Jupiter. It would be the only thing you could see in the daytime sky. It is a cosmic laser. It is a star on the edge of physics, and it is not alone. The Tarantula contains dozens of stars with masses over 50 solar masses. The environment in the Tarantula is so extreme that supernovae are a routine occurrence. Astronomers have confirmed at least 40 supernovae have exploded in the Tarantula region in the past 1 million years. 40! That is one explosion every 25,000 years. That is a prodigious rate of destruction. The entire region is a churning, boiling cauldron of expanding supernova remnants, shockwaves, and newborn stars. And we have a front row seat to one of them. In 1987, a star in the Tarantula Nebula exploded. It was supernova 1987A. It was the closest supernova to Earth since the invention of the telescope, and it has been studied relentlessly ever since. The shockwave from that explosion is still expanding. It is slamming into the surrounding gas and dust that was ejected by the star in its final years. We can see it. We can watch the ring of debris glow as the shockwave hits it. We are watching the aftermath of a stellar death in real time, and it is happening in the most violent nursery in the sky. 30 Doradus is a window into the past. It is a template. It shows us what star formation looked like in the early universe, when the cosmos was younger, when gas was much richer in hydrogen and helium, and much poorer in heavier elements. Back then, stars could become much more massive. They could reach 200, 300, maybe even more solar masses. They lived for a pittance of time, mere millions of years, and then they died in the most spectacular explosions the universe can produce, seeding the cosmos with heavy elements that would eventually make planets, and people, and the ability to look back and ask these questions. These are the major battlegrounds: the molecular ring, the central molecular zone, Sagittarius B2, the Fermi bubbles, Orion, Carina, and the Tarantula. They are not just interesting places on a map of the sky, they are the front lines. They are the places where the Cold War between gravity and energy, between creation and destruction, is being fought with the most ferocity. They are the factories, the graveyards, and the crucibles of the galaxy. And the war that is happening in these places is not separate from us. We are made of the dust that was forged in the heart of a star that exploded in Carina, or Orion, or some other forgotten battleground billions of years ago. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was manufactured in these conflicts. We are the survivors of a war that has been raging since the dawn of time. We have stood in the great arenas. We have watched the molecular ring churn with the birth pangs of 1,000 stars. We have felt the gravitational tyranny of Sagittarius A star over the entire central molecular zone. We have seen the ghostly photographic negative of the Fermi bubbles, the scars of a galactic eruption. We have looked into the nursery of Orion and watched the trapezium murder its own children with ultraviolet fire. We have seen the ticking bomb of Eta Carinae and the impossibly vast and violent Tarantula Nebula, a place where the old rules of stellar physics seem to break down entirely. But a battlefield is not just a collection of explosions. It is a landscape shaped by the ebb and flow of conflict. To understand the Milky Way, we must understand the structure that hosts all this violence. We must look at the spiral arms. The spiral arms of a galaxy are not solid structures. You cannot hold them. They are not like the spokes of a wheel. They are density waves. Think of a traffic jam on a highway. The cars are the stars. The traffic jam, the region of slow-moving, dense traffic, is the spiral arm. The cars are constantly entering the traffic jam from behind, crawling through it and then speeding out of the front. The cars themselves are not stuck in the jam forever, but the jam itself, the pattern of density, persists. That is a spiral arm. It is a wave of increased gravitational density that sweeps around the galaxy. Now imagine the gas. The giant molecular clouds, the supply depots of the galactic army, are the big, slow-moving trucks in this traffic jam. As they drift into the spiral arm, they hit the traffic. The density wave compresses them. The gravity of the wave pulls on them. This compression is the trigger. It is the starting pistol for the race to collapse. The spiral arms are the primary spawning grounds of the Milky Way. They are the conveyor belts of star formation. We sit in one of these spawning grounds. Our Sun is located in a relatively small, somewhat fragmented spiral arm called the Orion Arm or the Orion Spur. It is not a major arm. It sits between two much larger arms. The Perseus Arm, which is closer to the galactic centre, and the Scutum Centaurus Arm, which is on the other side. We are in a back alley of the galaxy, a minor road off the main highway, and this has been crucial for our existence. Look at the Perseus Arm. It is the nearest major spiral arm to us. When we point our radio telescopes at it, we see a level of star formation that dwarfs anything in our own neighbourhood. The W3 Giant Molecular Cloud Complex, for example, is a vast factory in the Perseus Arm that is birthing stars at a furious rate. It is a place of immense radiation and violence. If our Sun had been born in the Perseus Arm, it would have been in a much denser, more chaotic environment. The probability of a nearby supernova going off close enough to sterilize a developing biosphere would have been dramatically higher. The gravitational perturbations from passing stars would have been more frequent, potentially disrupting the Oort cloud and sending comets raining into the inner solar system at a catastrophic rate. We are here, in part, because we are in a quiet neighbourhood. Our Orion Spur is a relatively low-density, low-violence region. It is a safe house in the middle of a war. But even our safe house has seen action. The Sun was born in a star cluster, almost certainly in a giant molecular cloud that has long since been destroyed by the very stars it created. We have drifted away from our siblings. We have completed over 20 orbits around the galactic centre since we were born. And in that time, we have passed through the spiral arms multiple times. This is a sobering thought. As the Sun orbits the galaxy, it moves up and down like a carousel horse through the galactic plane. Sometimes it is above the plane, in the relatively sparse halo. Sometimes it dips back down into the dense, dusty disk, and every few 100 million years it passes through a spiral arm. When it does, we hit the traffic jam. The density of interstellar gas and dust increases. The flux of cosmic rays increases. The Oort cloud gets stirred up. Some believe that these passages through the spiral arms are linked to mass extinction events on Earth. The theory is that the increased cosmic radiation and the increased frequency of comet impacts caused by the gravitational stirring could have periodically stressed the biosphere, driving rapid evolution or causing sudden die-offs. This is a hypothesis, not a proven fact. The evidence is still being debated, but the logic is compelling. Our planet is not an isolated island. It is a ship sailing through a galaxy at war. Its course takes it through regions of relative peace and through regions of active combat. The history of life on Earth may be intimately tied to the history of the Milky Way's spiral arms. We are not just observers of the war, we are its passengers. And the war is not static, it has a history. The Milky Way we see today was not the Milky Way of 1 billion years ago, and it will not be the Milky Way of 1 billion years from now. The galaxy itself is evolving. The rate of star formation is slowing down. The giant molecular clouds are being consumed faster than they are being replenished. The supply of fresh, pristine gas falling into the galaxy from intergalactic space is dwindling. Look at the Small Magellanic Cloud, another dwarf galaxy orbiting the Milky Way. It is a distorted, tortured shape. We can see long streams of gas being pulled out of it by the tidal gravity of the Milky Way. That gas is being stolen. It is being funneled into our own disk, feeding the star formation in our spiral arms. This is a form of galactic cannibalism. The Milky Way is eating its neighbours. It has done this for billions of years, swallowing smaller galaxies and using their gas to make new stars. This is the ultimate expression of the Cold War. The galaxy itself is a predator, growing fat on the remains of smaller systems. But the doom of the giant molecular clouds is also the doom of the spiral arms themselves. As the gas is used up, the star formation rate will decline. The bright, massive blue stars that illuminate the spiral arms will die out, and they will not be replaced. In billions of years, the Milky Way will become a quiet, red galaxy. The spiral arms will fade. The war will end, not with a bang, but with a slow, cold exhaustion. The galaxy will fall asleep. But that is a distant future. The war is still raging. We have looked at the big picture. We have to zoom back in to see the most intimate, most personal form of violence. We have to look at binary star systems. Most stars in the Milky Way are not alone. They are born in multiple systems. About half of all Sun-like stars are in binary or triple systems. For massive stars, the fraction is even higher, approaching 100%. And this is a recipe for disaster. A binary star system is not a peaceful dance of two partners. It is a wrestling match. It is a gravitational cage fight. Think of the two stars as they orbit each other. They are born close together, often in the same disk of gas. As they age, they evolve. One of them, the more massive one, will run out of fuel first. It will swell up into a red giant. Its outer layers will expand, and if the two stars are close enough, the giant's atmosphere will spill over onto the companion. It is an act of stellar vampirism. The smaller star siphons hydrogen from the dying giant. This can trigger cataclysmic events. The transferred hydrogen can accumulate on the surface of the companion star until it reaches a critical pressure and ignites in a runaway thermonuclear explosion. We see these as novae. They are not full stellar destruction, but they are immense surface explosions that can briefly outshine the entire star. If the white dwarf core of the dead star is left behind and the companion keeps feeding it, the white dwarf can be pushed over a critical mass limit, the Chandrasekhar limit. When that happens, the pressure becomes so immense that the entire star collapses and detonates in a Type Ia supernova. This is a complete annihilation. The white dwarf is vaporized. It leaves nothing behind. These supernovae are the standard candles of cosmology, the beacons we use to measure the expansion of the universe. But for the stars involved, it is a murder-suicide pact. And then there are the black holes. If the companion is massive enough, when it explodes, it leaves behind a black hole. The binary system then becomes a black hole orbiting a normal star. If they are close enough, the black hole will start to feed on the star. Gas spirals into the black hole, heated to millions of degrees, emitting powerful X-rays. These are the X-ray binaries. They are the most luminous X-ray sources in the galaxy. They are cannibalistic systems. One partner is a dark, invisible predator, and the other is a bright, dying victim, being torn apart and consumed. And if two black holes are born in a binary system, that is the ultimate. They orbit each other, slowly spiraling inward over billions of years, radiating energy away as gravitational waves. Eventually, they will merge. When they do, they will send a ripple through space-time that we can detect with our instruments. A chirp of energy equivalent to the mass of several suns, all released in a fraction of a second. We have already heard these chirps. They are the sound of the most violent events in the universe, the final endpoint of the Cold War between two objects of pure gravity. From the largest structures to the smallest interactions, the theme is the same. The Milky Way is a place of conflict. It is a place where gravity, the ultimate force of attraction, is constantly pitted against the explosive violence of nuclear fusion and the expansive pressure of radiation. It is a system that is perfectly balanced between creation and destruction. The death of one star births the next. The corpse of a supernova provides the iron for a future planetary core. The radiation that boils away a proplide in Orion may be the very same radiation that enriches a neighbouring cloud, triggering a cascade of new star formation. The Cold War is not a war of good versus evil. It is not a war with winners and losers. It is a war that defines existence itself. We are here because of it. Our atoms were forged in its furnaces and scattered by its bombs. Our planet orbits a star that is a product of its cycles. Our very consciousness is a local, temporary, and fragile order that has arisen out of the chaos of this cosmic conflict. The Milky Way is not a peaceful pinwheel. It is a storm, and we are, for a brief moment, riding the wave. The war is not over. It will never be over. It is the only way the universe knows how to make a world. And yet, for all this talk of war and chaos, there is a persistent idea, a kind of comforting myth, that under it all, something simple is in charge. That the universe, in its grandest movements, is essentially a lazy place. That gravity, the great and steady pull of all things toward all other things, is the sole commander of the cold, dark clouds where stars are born. It is a neat, tidy, and utterly false limit. It suggests that these massive molecular clouds, these drifting cities of gas and dust, are just waiting, patiently, for the inevitable. That given enough time, gravity will win, the cloud will collapse, and a star will switch on, like a light bulb triggered by a simple switch. But if you look at the real sky, the one that hovers above us with its silent and stubborn complexity, you will see that the switch is broken. The collapse is not inevitable. The journey from a wisp of hydrogen to a roaring sun is not a gentle fall. It is a battle, a screaming million-year stalemate where every inch of ground is contested. And gravity, for all its cosmic muscle, is not alone in the ring. So let us dismantle this false limit, piece by piece. The first and most immediate counterpunch to gravity's dominance is turbulence. We are not talking about the gentle bumpiness you feel in an airplane. We are talking about supersonic chaos. Inside a giant molecular cloud, the gas is not sitting still. It is screaming. It is moving in every direction at once, with speeds that break the sound barrier. Imagine standing in the middle of a hurricane, but the air is moving faster than a bullet, and it's cold enough to freeze the oxygen right out of your lungs. That is the normal state of affairs inside a star-forming region. These supersonic flows, driven by the shock waves from dying stars, the winds of newborn giants, and the sheer gravitational jostling of the cloud itself, create a kind of pressure. It is a dynamic pressure, a force that pushes back against gravity. Think of it like trying to compress a bag of angry cats. Every time gravity tries to squeeze a parcel of gas together, the turbulence shoves it apart, stirring the pot, shredding the densest knots, and slowing the collapse to a crawl. This is not a minor effect. It is the primary reason why most of the gas in a molecular cloud never forms stars. The cloud is not a monolithic blob waiting to crumble. It is a churning, frothing mess of competing currents, and gravity has to fight for every single collapsing core it gets. But turbulence is only the first line of defense. The universe has a second, more insidious weapon in its arsenal: magnetism. Our galaxy is threaded with magnetic fields, invisible lines of force that stretch across light years. These fields are incredibly weak by earthly standards, but over the vast scales of a molecular cloud, they are anything but insignificant. They are like a spider web, woven through the gas and dust. Now, here is the trick. These magnetic fields are not attached to just anything. They are coupled to electrically charged particles. In the cold depths of space, most of the gas is neutral, made of plain, uncharged atoms of hydrogen and helium. But there is a small fraction, maybe one particle in 10,000, that is ionized. It has lost an electron. It is charged. And these charged particles are the puppets of the magnetic field. They are forced to dance along the invisible lines, stuck in place, unable to cross from one field line to the next. So far, so good. But what about all the neutral gas? The heavy, uncharged hydrogen that makes up the vast majority of the cloud? It wants to collapse. It feels the pull of gravity. But the charged particles, locked to the magnetic field, act like a wall. They bump into the neutral atoms, slowing them down, creating a drag. It is like trying to run through a crowd of people who are all holding hands. You can push, but the whole crowd shifts together. This is the phenomenon of magnetic support. The field lines, anchored to the ionized gas, resist being compressed. They act like a spring. The more gravity tries to squeeze the cloud, the more the magnetic field lines bunch up, and the stronger their resistance becomes. For a long time, astronomers thought this might be the ultimate checkmate, that gravity could never win, that the magnetic field would hold the cloud up forever, preventing any collapse at all. But then they realized something. The neutral atoms are stubborn. They can slip through the cracks. The neutral particles, in their relentless drift toward a gravitational center, can slowly, agonizingly slowly, move past the magnetic barrier. They are not stopped completely. They are just delayed. This process is called ambipolar diffusion. It is the hero of this part of the story, or perhaps the traitor, depending on your point of view. The neutral hydrogen atoms, the stuff of future stars, are not bound to the magnetic field. They feel only the pull of gravity and the gentle push of collisions with the charged particles. Over millions of years, a neutral atom will bump and jostle its way, drifting like a ghost walking through a wall, past the magnetic field lines. It is a glacial process, a crawl measured in centimeters per second. But over a million years, those centimeters add up. The neutral gas slowly, methodically, leaks into a central region, forming a dense core that the magnetic field can no longer protect. The spring begins to sag. The wall starts to crumble. Gravity, patient as death, waits for the leak to become a flood. And then, when enough mass has gathered, the magnetic field is overwhelmed. The field lines snap, and the cloud core collapses. But do not be fooled into thinking this is a gentle process. It is not a smooth, gradual settling. It is a final violent collapse after a long, grinding war of attrition. So here we have the three-way standoff. Gravity, the commander; turbulence, the chaotic shock trooper; and magnetism, the stubborn guerrilla fighter. The fate of every star, every planet, every world that will ever be is decided by which of these forces wins the argument in any given pocket of the galaxy. Gravity is the ultimate long-range force. It will eventually win. That is the tragedy of the universe. But it does not win easily, it does not win everywhere, and most importantly, it does not win gently. The false limit is the idea that star formation is a slow, peaceful, inevitable process, that you pour a bunch of gas into a cloud, wait a few million years, and out pops a sun. That is a lie. The reality is far more violent and far more surprising. Think about what actually triggers the final collapse. The cloud is sitting there in a delicate balance. The turbulence and magnetism have held off gravity for millions of years. But then, something happens. A shockwave arrives. Perhaps a nearby supernova, a star at the end of its life that has exploded, sends a blast wave tearing through the interstellar medium. This shockwave slams into the side of the molecular cloud. It compresses the gas. It shoves it together. All of a sudden, the density in one region skyrockets. The balance is shattered. The magnetic field, already stretched thin, is overwhelmed. The turbulence for a brief moment is outmuscled by the external pressure, and gravity, which had been waiting in the wings, takes the opportunity. It seizes the newly compressed gas and pulls it in. This is not a fall. This is an ambush. It is a trigger. That is how most stars are born. Not by the slow, gentle leaking of ambipolar diffusion, but by the violent, sudden hammer blow of a stellar wind from a nearby giant, or the shockwave from a dying star, or the collision of two entire clouds. Star formation is a triggered event. It is a chaotic chain reaction. One star dies, its explosion compresses a cloud, 100 new stars are born, and some of those will be massive. Those massive stars will burn fast and die young. They will explode, triggering the collapse of yet another cloud. The whole spiral arm of the galaxy is a cascade of explosions and births, a chain of violence that feeds on itself. This is the part of the story that we as humans get wrong so often. We look at the night sky and see serenity. We see twinkling lights, calm and eternal. We imagine the process that made them to be equally serene. A gentle gathering of dust, a quiet ignition, a soft, glowing nursery. No, the nursery is a war zone. The cradle is a battlefield. The clouds are full of shock waves and magnetic storms. The gas is supersonic. The collapse happens not because it is easy, but because external forces make it impossible to resist. The star is born in a moment of violence, its first breath, the shock of compression. And even then, the fight is not over. The new star will scream. It will launch its own winds and jets, pushing back against the falling gas, trying to stop the very collapse that created it. The infant star fights its own birth, blasting away the material that feeds it. It is a paradox. The star needs the gas to fall in to grow, but its own light and heat create a pressure that tries to push the gas away. This is called radiation pressure, and for massive stars it is a powerful force. It is another layer of the standoff. The star once born becomes its own enemy. So the false limit crumbles. It is not gravity alone. It is gravity, held at bay by turbulence, stymied by magnetism, leaking through ambipolar diffusion, and then finally winning only because a supernova punched the gas in the face. The entire process is a brawl, and the implications are staggering. It means that the number of stars in the galaxy, the rate at which they form, is not a simple function of the amount of gas. It is controlled by a delicate, chaotic balance of forces. Change the magnetic field strength, or the level of turbulence, or the rate of supernovae, and you change the entire stellar census. You change the fate of the galaxy. This is why we cannot predict star formation with a simple formula. We have to simulate it with supercomputers, trying to track every shockwave, every magnetic field line, every drifting neutral atom. And even then, the models are rough approximations. We are trying to understand a storm by drawing a picture of a single raindrop. There is another, deeper, more humbling implication. The false limit is not just about physics. It is about our own tendency to simplify the universe. We want the universe to be simple. We want a single law, a single force, a single path from cause to effect. But the universe resists this. It is messier than our theories. It is more stubborn. The very existence of our sun, of our planet, of you and me, is a testament to a billion improbable victories. It is the result of gravity winning a fight it had no business winning. The gas that made our sun had to survive the turbulence. It had to slip past the magnetic field. It had to be hit by the right shockwave at the right time. And then it had to collapse without being blown apart by its own newborn light. Every star is a miracle of defiance. Every star is a survivor. And we, made of star stuff, are the children of that cosmic brawl. The war is not over, it never will be. But out of the chaos, out of the standoff, out of the grinding battle between gravity, magnetism and turbulence, something beautiful and temporary is born. A star, a world, a life, and that perhaps is the most astonishing thing of all. All right, let's be honest for a second. If you were to picture a war between two opposing forces, you'd imagine a clash that goes on forever, right? Two sides that just keep pounding away at each other until one finally breaks. That's how we usually think of conflict. But the war between gravity and the cosmos doesn't always play out that way. Sometimes the battle ends before it can really begin, and that's because of something we need to call the true limit. A limit that isn't imposed by a lack of raw material or a shortage of gas. The true limit is the stars themselves. The moment a star is born, it begins to attack its own cradle. Think about it. You've got this massive cloud of gas and dust, maybe 100 light years across, sitting there in the cold, dark void of space. It's peaceful. It's quiet. It's a nursery that's waiting for the first spark. Then gravity does its thing. A few clumps start to pull in more material, and the temperature rises and the pressure builds. And then, boom, nuclear fusion ignites. A star is born. But here's the kicker. That star doesn't just sit there glowing nicely. It immediately starts throwing a fit. It starts screaming at the very cloud that gave it life. This is the feedback loop, and it's vicious. The first attack comes in the form of ultraviolet radiation. Now you and I, we think of UV light as something that gives us a sunburn if we're not careful. But out in the cold vacuum of space, that UV light is a weapon of mass destruction. When a massive star turns on, it blasts out an insane amount of high-energy photons. And these photons don't just fly off into space harmlessly. They slam straight into the surrounding hydrogen atoms, and when they do, they strip the electrons right off those atoms. This is photoionization. It sounds technical, but it's really just a cosmic punch to the face. The hydrogen atom is now a charged ion, and it's angry about it. But the real damage doesn't come from the stripping of the electrons. It comes from the heat. Because when that ionization happens, it raises the temperature of the gas from a bone-chilling 10 degrees above absolute zero, 10 Kelvin, to a blistering 10,000 Kelvin. 10 degrees to 10,000 degrees. That's not a gentle warm-up. That's a nuclear furnace belching fire into a room full of gasoline. And when you heat gas that much, it does what any sane gas would do. It expands. It expands violently. And I mean violently. We're talking about a 1,000-fold increase in volume. That sphere of superheated gas, that's called an HII region, and it's not just a pretty red blob you see in pictures. It is a supersonic shockwave that slams into the surrounding cloud. This HII region expands at speeds faster than sound. It rips through the cloud like a shockwave from an explosion. It carves out a giant bubble in the middle of the molecular cloud. And as this bubble grows, it pushes all the gas and dust ahead of it. It compresses that material into a thin, dense shell. And here's where it gets weird. That compression, that violent pushing and shoving of matter, it actually triggers new star formation. You see, the same force that is destroying the original cloud is also squeezing new pockets of gas so hard that they collapse and start forming new stars. This is what we call triggered star formation. And it is a double-edged sword if there ever was one. You get this cascade effect. The first massive star blows a hole in the cloud, which compresses the edges, which creates new massive stars, which blow new holes, and on it goes. It's a chain reaction of creation and destruction that is almost beautiful to watch. But here is the brutal truth. The original cloud doesn't survive this process. It gets shredded, it gets torn apart. The gas that was once a peaceful nursery is now being kicked and beaten and scattered to the four winds. And the most famous example of this carnage is right in our own backyard. You've seen the pictures, the pillars of creation in the Eagle Nebula. You know them. Those towering fingers of dust and gas that look like ancient monoliths reaching out into the void. They are some of the most iconic images in all of astronomy. But here is the part that most people don't know. Those pillars are dying right now. They are being evaporated. As we speak, the intense radiation from nearby massive stars is boiling away the gas that makes up those pillars. It's like a blowtorch held against an ice sculpture. The pillars are dissolving, and they are not going to be around for long. In astronomical terms, they will disappear in the blink of an eye. Give it about 100,000 years. That sounds like a long time to us, but in the life of a galaxy, that is nothing. A single human lifetime across the cosmic calendar. But here is the really tragic part. Inside those pillars, young stars are still trying to form. They are still trying to gather enough mass to switch on their own fusion. But they are running out of time. The clouds are being stripped away faster than the stars can feed. They are like a baby trying to drink milk from a mother that is being dragged away. These stars may never finish forming. They will be orphaned. They will be left as stellar embryos, frozen in time, never reaching the point of ignition. All that potential, all that mass, all that work that gravity put in, wasted, because of feedback. So let's talk about the numbers. The raw math of this war is actually kind of depressing if you are a fan of star formation. When you look at a giant molecular cloud, a GMC as we call them, you have to realise that it is incredibly inefficient. I mean, it is laughably inefficient. The star formation efficiency of these clouds is only between 1 and 10%. Let me say that again. 1 to 10%. That means that out of all the gas and dust in a giant molecular cloud, at best, only 10% of it ever becomes a star. The other 90 to 99% of the cloud is just thrown away. It is expelled. It gets kicked back out into the interstellar medium. Think about that for a second. You have this massive engine of gravity, this unstoppable force that pulls matter together for millions of years. And then, when the star finally turns on, it immediately destroys 90% of its own fuel source. It spits it back out. It's like building a house, and then taking a sledgehammer to the walls as soon as you put the roof on. It makes no sense from a human perspective, but from a cosmic perspective, it is the only way the galaxy works. This feedback mechanism is the pressure release valve. It's what stops the whole galaxy from collapsing into a single monstrous black hole. But that expelled gas doesn't just disappear. It floats away, it drifts into the void, and then over time it starts to cool. It takes millions of years for that hot ionized gas to shed its energy and drop back down to that bone-chilling 10 Kelvin. Once it is cold enough, it starts to clump up again. It gets swept up by galactic currents and shockwaves from other supernovae. And then, slowly, over 100 million years, it gathers back together to form a new molecular cloud. A new nursery. A new battlefield. So the cycle continues. The war is not over, but it is constantly resetting itself. And that brings us to the truly brutal limitation. The lifespan of a molecular cloud. These giant nurseries don't last long. They are fragile. They are temporary. The average molecular cloud lives for only about 10 to 50 million years. That sounds like a long time, but compared to the life of a star like our Sun, which will burn for 10 billion years, it is a snapshot. It is a flicker. And here is the problem. Most of these clouds are destroyed by their own massive stars, long before they have a chance to convert even a fraction of their mass into new suns. They are self-destructive. You get a cloud. It collapses. A few massive stars ignite, and those massive stars, they are the firecrackers. They burn hot and fast and loud, and within just a few million years they blow the whole thing apart. The cloud is gone. The raw material is scattered, and the remaining low-mass stars, the ones that didn't get the memo, they are left behind to fend for themselves. So the true limit is not a lack of hydrogen. The universe is swimming in hydrogen. The true limit is time. It is the feedback loop. The stars themselves refuse to let the process continue. It is like a rebellion. The children kill the parents. The created destroy the creator. And on the local scale, the scale of a single cloud or a single cluster, the war is self-terminating. It burns out. It stops itself before it can go too far. Gravity tries its hardest, but the stars are just too violent. They are too chaotic. They push back with so much force that the whole system gives out. It is not a strategic retreat. It is a violent collapse. So what does that mean for us? It means that the production of stars is not a smooth, steady process. It is a stuttering, sputtering, messy affair. It is a series of short, violent bursts, followed by long periods of quiet. And it means that most of the matter in the galaxy is just going to sit there, cold and inert, waiting for the next wave of turbulence to sweep it into a new cloud, where the whole dance will start again. The galaxy is a recycling machine. It takes the leftovers of one generation and uses them to build the next. But it is a wasteful machine, an inefficient machine. But you know what the crazy part is? Despite all this waste, despite all this inefficiency, despite the fact that 9 out of every 10 molecules of gas never make it into a star, despite the fact that the clouds evaporate before they are finished, despite all of that, the universe still manages to make stars. It still manages to make planets. It still manages to make life, and that is the miracle. That is the thing that makes this whole chaotic mess worth it. The universe is fighting itself, wasting its own resources, blowing up its own nurseries, and yet, somehow, against all odds, a little spark of life can still flicker into existence on a tiny rock orbiting a yellow star in the outskirts of an average galaxy. So the next time you look up at the night sky, remember the war, remember the violence, remember the supersonic shockwaves and the 10,000-degree heat, but also remember the survivors, the stars that endured, the planets that formed in the debris, and the fact that you are here, listening to this, a living testament to the fact that even in a war that is self-terminating and brutally inefficient, the cosmos can still produce something that is capable of looking back and wondering how it all began. The true limit is not a wall, it is a sieve, and through that sieve, against all logic, beauty still pours through. Now, if you really want to understand the scale of this self-terminating war, you have to look at where these wars are fought. You have to look at the most extinct nurseries in the galaxy. And you have to look at something called the Tarantula Nebula. It is a star-forming region in the Large Magellanic Cloud, a satellite galaxy orbiting our own Milky Way. The Tarantula Nebula is a monster. It is the most violent, most luminous, most massive star-forming region in the entire local group of galaxies, and it is a perfect case study in how the war ends before it can really begin. The Tarantula Nebula is home to a cluster of stars called R136, and R136 is not your typical cluster. It contains hundreds of the most massive stars ever discovered. We are talking about stars that are 50, 100, even 200 times the mass of our Sun. These are not stars. They are stellar bombs waiting to go off. They burn through their fuel in a matter of a few million years, and while they are alive, they are the most destructive force in the galaxy. The amount of ultraviolet radiation pouring out of R136 is almost incomprehensible. It is enough to ionize the entire Tarantula Nebula, creating a bubble of hot gas that is hundreds of light years across. And here is where you see the self-terminating nature of the war in its most dramatic form. The radiation from R136 is so intense that it is literally blowing the nebula apart. It is carving out a cavity in the center, a void where no new stars can form. The gas that was once there is now a thin, hot plasma drifting away at supersonic speeds. The nursery is being gutted from the inside, and the stars that are trying to form on the edges of the nebula are being squeezed. They are being compressed by the advancing shockwave, and some of them will collapse and ignite. But most of them will not. Most of them will be left as failed stars, as brown dwarfs, as cold, dark objects that never reached the threshold of fusion. The Tarantula Nebula is a war zone, and the casualty rate is staggering, but it is also a laboratory. It is a place where we can see the process of star formation in its rawest, most brutal form. And it teaches us something important. It teaches us that the true limit of star formation is not just the feedback from a single star. It is the collective feedback from a cluster of stars. When you pack hundreds of massive stars into a small volume, the combined effect is orders of magnitude greater than anything a single star could produce. The cluster becomes a single unified weapon of mass destruction, and it turns the entire nursery into a wasteland. So now we have to ask a different question. If the war is so brutal, if the feedback is so destructive, how does the galaxy manage to produce stars at all? How does it overcome its own self-terminating nature? And the answer is something we call the interstellar medium. It is the stuff between the stars, the gas and dust that fills the vast spaces of the galaxy. And it is not uniform, it is clumpy, it is turbulent, it is a chaotic mess of different temperatures, densities, and velocities. And that chaos is what allows star formation to survive. Think of the interstellar medium as a giant roiling ocean. There are currents, there are eddies, there are regions of calm and regions of storm, and in the densest, coldest pockets of this ocean, gravity can gain a foothold. It can pull together enough material to form a molecular cloud before the feedback from other stars can blow it apart. And once that cloud is formed, it is shielded. The dust within the cloud absorbs the ultraviolet radiation, preventing it from penetrating too deep. The cloud becomes a fortress, and inside that fortress, stars can form in relative peace, at least for a while. But the fortress is not permanent. The most massive stars inside the cloud will eventually punch through the shield. They will create holes in the dust. And once those holes are open, the radiation floods in and the war begins anew. So the true limit of star formation is not a single number. It is not a single process. It is a dynamic balance between collapse and dispersal. It is a dance between gravity and feedback. And that dance plays out on every scale, from the smallest cloud to the entire galaxy. And here is the most profound part of this war. The galaxy itself is a self-regulating system. It is a machine that balances the rate of star formation against the rate of feedback. If too many stars form, the feedback from those stars will heat up the interstellar medium, preventing further collapse. If too few stars form, the interstellar medium will cool and become dense, allowing new clouds to form. It is a feedback loop on a galactic scale, and it means that the galaxy is in a state of equilibrium. It is not growing. It is not shrinking. It is just cycling matter through stars, one generation after another. But this equilibrium has a name. It is called the Kennicutt-Schmidt law. It is a relationship between the density of gas in a galaxy and the rate at which that gas forms stars. And the law is simple. The denser the gas, the faster the star formation. But it is not linear. It is a power law. It means that a small increase in gas density leads to a much larger increase in star formation. And it means that the galaxy is exquisitely sensitive to its own structure. If you compress the gas, you get a burst of star formation. If you expand the gas, you get a lull. And that sensitivity is what makes the war so brutal. Because the feedback from a burst of star formation can trigger a chain reaction that propagates through the entire galaxy. It can create waves of star formation that move across the disk like ripples in a pond, and those waves can be so powerful that they distort the shape of the galaxy itself. They can create spiral arms. They can create bars. They can create rings of intense star formation that resemble fireworks. It is a beautiful and terrifying spectacle, and it is a testament to the power of the war between gravity and the cosmos. But here is the tragedy. The war is not only self-terminating on the scale of a single cloud, it is also self-terminating on the scale of the entire galaxy. The galaxy has a finite amount of gas, and every time a star is born, that gas is locked up for billions of years. It is taken out of the cycle, and every time a star explodes, it returns some of that gas to the interstellar medium, but it also heats it up, making it harder to form new stars. So the galaxy is slowly running out of fuel. It is slowly starving itself. It is a slow-motion suicide. We live in a galaxy that is in its middle age. The Milky Way is still producing stars, but the rate has been declining for billions of years, and it will continue to decline. Eventually, in about 100 billion years, the gas will be too thin, too hot, too diffuse to form any new stars at all. The galaxy will become a cemetery, a collection of dim, dying stars and cold, dark remnants. The war will be over, gravity will have lost, and the cosmos will be silent. So the true limit of star formation is not just the feedback from the stars themselves. It is the finite supply of raw material. It is the inexorable march of entropy. It is the fact that every star that forms is one step closer to the end. And that is the most profound thing of all. The war is not just brutal. It is not just inefficient. It is not just self-terminating. It is also finite. It has a definite end. The universe will eventually stop making stars. And when it does, the cosmos will enter a long, dark, cold night from which there is no awakening. That is the true limit. That is the ultimate tragedy. And that is the price we pay for the stars. And so we arrive at the final act. The long view. The view from the edge of time, where the fates of these stellar soldiers are decided not in a single explosive moment, but over billions upon billions of years. You see, the Cold War between stars is not just a war of birth and death. It is a war of environment, of location, of cosmic real estate. Because where a star is born determines, to a staggering degree, whether it will be a victor, a survivor, or a loser. Think about it. A star born in isolation, a lonely wanderer in the galactic void, has a very different life than one born in a dense, chaotic cluster. It is like comparing a hermit living in a remote cabin to a child raised in a bustling, violent city. The environment leaves permanent marks. It scars the star's mass, its trajectory, its very destiny. And the universe, it turns out, is a deeply unfair place. Let's start with the numbers. The initial mass function. It is the cosmic rulebook that dictates how many stars of each size are born. And the rulebook is brutally tilted toward the small. For every single star that is 10 times the mass of our Sun, there are roughly 1,000 stars that are just one solar mass. And for every one of those 1,000 sun-like stars, there are even more of the tiny ones, the red dwarfs. The universe loves the little guys. It churns them out by the billions. Massive stars are the rare, glamorous superstars, burning bright and dying young. The small ones are the workhorses, the quiet majority. But the war does not start with the star itself. It starts with the nursery. Most stars are not born in isolation. Roughly 90% of them are born in clusters. Not the enormous globular clusters you might be picturing, but smaller, embedded clusters. 100, maybe 1,000 members. A tight, cramped, chaotic nursery of gas and dust and gravitational wrestling. And here is the first great tragedy of the Cold War. These clusters are fragile, incredibly fragile. Within just 10 million years, a blink of an eye in cosmic terms, 90% of these clusters dissolve. They simply fall apart. The gas that held them together, the very stuff they were born from, gets blasted away by the most massive stars in the cluster. These young giants unleash furious stellar winds and erupt in supernovae. And when the gas is gone, the glue is gone. The cluster becomes unbound, and the stars are set adrift. But some are not just set adrift. Some are kicked out, violently. Dynamically, this is where we meet the runaways, the OB stars. Stars like Zeta Puppis. This star is a monster, a Class O supergiant, incredibly hot and luminous, weighing in at more than 50 times the mass of our Sun. And it is moving at a staggering speed, hurtling through space at over 60 kilometers per second. Why? Because it was expelled from its natal cluster. A close encounter with another massive star, a gravitational slingshot, and suddenly Zeta Puppis was no longer a cluster member. It became a lone wolf, a rogue, an exile. These runaway stars are common. They are the cosmic equivalent of teenagers getting kicked out of the house, forced to make their way in the galaxy on their own. Some will live out their short, brilliant lives in solitude. Others, if they are slow enough, might eventually find a new home, drifting into another cluster and becoming an outsider looking in. But for every star that gets expelled, there are others that never even got the chance to be a star. And these are the losers, the failures. We call them brown dwarfs. They are the objects that were born with too little mass to ever ignite hydrogen fusion in their cores. They are stuck in a kind of perpetual adolescence, forever cooling, forever dimming, never quite reaching the threshold of true stellar life. To be a star, you need to reach a critical mass. You need to squeeze your core hard enough, hot enough, to fuse hydrogen into helium. That threshold is roughly 80 times the mass of Jupiter. If you fall short, even by a little, you are doomed to be a brown dwarf. You will emit a faint reddish glow for a while, powered by the fusion of deuterium, a heavier isotope of hydrogen. But that phase is brief. After that, you just cool down, and you keep cooling for eternity. The coldest known brown dwarf is an object called WISE 0855-0714. Its temperature is just 250 Kelvin. That is minus 23 degrees Celsius. Minus 10 degrees Fahrenheit. It is so cold that its atmosphere is mostly water vapour and methane. It is a world of frozen clouds and frigid skies, a failed star wandering the darkness. And there are billions of them out there. More brown dwarfs than there are normal stars. They are the quiet, invisible majority, the ones who lost the war before it even began. But the most tragic losers of all might be the ones you have never heard of. The orphaned planetary mass objects. Imagine a gas giant planet like Jupiter. Now imagine it never got a chance to be a planet. Instead, it was ejected from its young chaotic star system by the same kind of gravitational slingshot that kicked out Zeta Puppis. These are free-floating worlds, rogue planets, wandering the galaxy without a sun. They are cold, they are dark, and they are everywhere. Recent estimates suggest there might be billions of them in the Milky Way alone, drifting silently between the stars. They are the ultimate orphans, the forgotten children of the Cold War, doomed to eternal exile. But hold on, put all of this into a larger frame. Because all of this drama, all of this fighting and dying and failing, all of it is happening within a much larger structure that we cannot even see. Dark matter. It constitutes about 27% of the universe's energy content. It is invisible. It does not interact with light. We cannot touch it, we cannot see it, we can only feel its gravity. And yet, without dark matter, none of this would exist. None of it. Think of dark matter as the invisible scaffolding of the universe. It provided the gravitational wells that allowed the first galaxies to assemble. We talk about the cosmic web, those vast filaments of gas and dust that stretch across millions of light years. That web is made of dark matter. It is the skeleton. The gas and stars are just the flesh on the bones. Without dark matter, there would be no cosmic web. Without that web, molecular clouds could never have formed, and without molecular clouds, no stars. No war, no us. Dark matter is the reason the Cold War can even be fought. It held the universe together during its chaotic infancy. It gave the gas a place to settle, to cool, to collapse. It is the silent, invisible architect of everything we see, and it will be there long after the last star has died, a ghost in the machine, an eternal witness to the war it made possible. But even on a smaller scale, the Milky Way itself is a battlefield, a dynamic, ever-changing engine of star formation. Look at the galactic bar, that massive elongated structure of stars and gas that cuts across the centre of our galaxy. The bar is not just a pretty feature, it is a weapon. It drives gas inward, funneling it from the outer disk toward the galactic centre. It is a gravitational conveyor belt, herding clouds of molecular gas into the central molecular zone, a region of intense star formation and chaos around the supermassive black hole. The bar is a sculptor, shaping the flow of fuel that powers the galactic engine, and then there are the Lindblad resonances. These are regions where the orbits of gas clouds sync up with the rotation of the spiral arms. It sounds technical, but the effect is simple. It concentrates gas. It squeezes clouds together, forcing them to condense and collapse. This is what creates the molecular ring, a dense, star-forming ring that wraps around the galaxy about 15,000 light-years from the centre. The ring is a stellar nursery on an industrial scale. It is where most of the Milky Way's new stars are being born right now. But even our own galaxy is not an island. It is being tugged, pulled and torn by its neighbours. The Large Magellanic Cloud, a dwarf galaxy orbiting the Milky Way, exerts a powerful tidal force. It is distorting the outer disk of our galaxy, warping it like a piece of paper being bent by a giant hand. And it is stripping gas away from the Milky Way. That stripped gas forms the Magellanic Stream, a long trailing ribbon of hydrogen that stretches across hundreds of thousands of light years. It looks like a wound, a scar on the galaxy. But it is not a loss, it is a gift. That gas will eventually fall back into the Milky Way or into the Large Magellanic Cloud itself, fueling new generations of stars. It is a cycle of destruction and rebirth, a cosmic recycling program that has been running for billions of years. And then there is Andromeda, our nearest major galactic neighbour. In about 4.5 billion years, the Milky Way and Andromeda will collide. It sounds apocalyptic, and it will be for some stars, but for most it will be a gentle slow-motion dance. The spaces between stars are so vast that individual stars will rarely, if ever, collide, but the gas clouds will. They will slam together, compress and ignite. The collision will trigger a massive starburst, a final, glorious firework display of star formation. For a few 100 million years, the combined system will blaze with new light, a last hurrah before the gas runs out. That collision is the final major battle of the Cold War in our local patch of the universe. It is the grand finale. And after that, after the collision, after the starburst, after the last gas cloud has been consumed, what then? This is where we turn to the cosmological future, the long, slow decline. The universe is running out of fuel. Star formation is already declining. It peaked about 10 billion years ago, when the universe was a riot of star birth. Now it is a fraction of what it once was, and it will keep declining. The gas is being locked away. Some of it is blown out of galaxies by supernovae, some of it falls into black holes, the rest is slowly, steadily converted into stars. And those stars, once formed, lock that gas away for trillions of years. Think about it. In about 100 billion years, the last of the free gas will be gone. All of it will be locked inside stars, white dwarfs, neutron stars, and black holes. No more molecular clouds, no more collapsing filaments, no more protostars. The star formation era will be over. The universe will have made its last star. But the war is not quite finished, because the last stars, the smallest ones, the red dwarfs, will still be burning. These stars are incredibly frugal. They weigh in at maybe 10% of the mass of our Sun. They burn their hydrogen so slowly, so efficiently, that they can live for 10 trillion years. 10 trillion years. That is 1,000 times longer than the current age of the universe. These are the ultimate survivors. They are the old soldiers of the Cold War, the ones who will outlast everyone. They will sit there, dim and red, plodding along while the universe around them grows ever darker, ever colder, but even they will eventually fade. After 10 trillion years, even the smallest red dwarf will exhaust its hydrogen fuel. It will shrink, cool, and become a helium-white dwarf, a tiny, dense, cold ball of degenerate matter. And it will keep cooling. Forever. The last stars will die, not with a bang, but with a whimper. They will simply become too cold to emit any detectable light. They will join the ranks of the brown dwarfs, the orphaned planets, the dark matter. The universe will become a cold, dark sea of remnants. Black holes, white dwarfs, neutron stars, dead planets, and the invisible, eternal scaffolding of dark matter. That is the ultimate fate. The Cold War between stars will be over. There will be no more winners, no more losers. Just silence. Just darkness. Just the slow, relentless march toward thermodynamic equilibrium. Heat death. The universe will have reached its final state, a state of maximum entropy, where no more work can be done, no more energy can be extracted. It will be a universe of eternal, unchanging stillness. But that is not today. That is not even close to today. We are in the prime of the war. We are in the thick of it. Right now, in every molecular cloud, in every collapsing filament, in every nascent protostar, the war continues. The gas is falling, the cores are heating, the battles are being fought, the giants are being born, and they will die. The dwarfs are being formed, and they will endure. The runaways are being ejected, the orphans are being abandoned, and the war rages on. So look up at the night sky. Every star you see is a soldier in this war. Every nebula is a battlefield. Every dark void is a potential nursery waiting for its moment. The Cold War between stars is not a historical event. It is a living, breathing, ongoing conflict. It is the story of the universe. and we are part of it. We are made of the debris of this war. The iron in your blood was forged in a massive star that died billions of years ago. The calcium in your bones was scattered by a supernova. We are the children of the Cold War. We are the survivors, and as long as there is gas, as long as there is gravity, as long as there is dark matter holding it all together, the war will continue. It will not stop until the last star fades, and that, my friends, is a very, very long time from now. What you have just heard is the slow, inevitable decay of a universe running out of time and fuel. But to truly understand the Cold War, we must not just look at the end. We must look at the very beginning. We must look at the moment the first shot was fired. That shot was not a supernova. It was not the ignition of a massive star. It was the formation of the very first generation of stars, a generation so alien, so violent, and so critical to everything that followed that we call them population 3 stars. Before these stars, the universe was a simple place. It was a sea of hydrogen and helium with a tiny trace of lithium, that is all. No carbon, no oxygen, no iron, no calcium, no elements that we consider essential for life, or even for the formation of small, stable stars like our Sun. The universe was chemically pure and chemically boring, but it was also very, very dense. Not dense like a planet, but dense in a cosmological sense. The primordial gas clouds that formed after the Big Bang were massive. They were not the relatively small clumps we see in the Milky Way today. They were giants. They were millions of times the mass of the Sun, all gathered in one region, with no heavy elements to help them cool and fragment. This is the key point. Heavy elements, which astronomers call metals, are excellent coolants. They radiate heat away efficiently. Without them, a collapsing gas cloud gets hot, very hot, but it cannot shed that heat quickly enough to break apart into many small pieces. Instead, a single enormous clump forms. It collapses, it gets denser, it gets hotter, and when it reaches the critical temperature and pressure, it ignites. But not a small, stable fire, a monstrous raging inferno. The first stars were not like the stars we see today. They were titans. They were likely hundreds of times the mass of our Sun, possibly even 1,000 times. They were so massive that their surfaces were blue hot, blazing with ultraviolet radiation, so intense it could ionize the gas around them for thousands of light years. And they did not live long, for a star mass determines lifespan. A star like the Sun lives for 10 billion years. A star with 300 solar masses lives for perhaps 3 million years. That is a blink. They burned through their hydrogen fuel with insane voracity. They lived fast and they died hard. And when they died, they did not go quietly. They did not become white dwarfs. They did not become neutron stars. They collapsed directly into black holes. Or they detonated in hypernovae, explosions 100 times more energetic than a normal supernova. In these cataclysmic events, the first heavy elements were forged. The first carbon, the first oxygen, the first iron. They were scattered into the surrounding universe, seeding the pristine gas with the seeds of future generations. This was the first battle of the Cold War. The population 3 stars were the opening salvo. They cleared the cosmic fog. They ionized the neutral hydrogen that filled the universe, ending the cosmic dark ages. They built the first black holes, the seeds that would eventually grow into the supermassive monsters that lurk at the centers of galaxies. They created the chemical foundation for every star, every planet, and every life form that would follow. And then they were gone. Not a single one remains today. We will never see one in our telescopes. They are ghosts, known only by their fingerprints on the chemical composition of ancient metal-poor stars that were born from their ashes. But that is not the only kind of ghost we need to consider. The Cold War has left behind a graveyard. It is filled with the remnants of dead stars, and these remnants are not passive. They are not simply inert corpses. They are active players in the ongoing conflict. Consider the neutron star. It is the collapsed core of a massive star that went supernova, but was not quite massive enough to form a black hole. It is an object so dense that a teaspoon of its material would weigh billions of tons. Its gravity is immense. Its magnetic field is trillions of times stronger than Earth's. It spins often at hundreds of revolutions per second, and when conditions are right, it becomes a pulsar, a cosmic lighthouse, beaming radiation across the galaxy. But the most dramatic neutron star systems are those in binary pairs. Two massive stars are born together. They live their short lives. They both explode as supernovae, and if the explosions are not perfectly symmetric, the system gets a kick, it gets a hard shove. The two neutron stars are sent flying, but they remain bound to each other by gravity. They orbit a common centre, slowly spiralling inward. They lose energy by emitting gravitational waves, ripples in the fabric of space-time itself. The orbit shrinks, the speed increases, and eventually, after millions or billions of years, they collide. It is not a gentle meeting, it is a cataclysm, a kilonova, an event that releases more energy in a few seconds than the Sun will produce in its entire lifetime. In that brief, furious moment, the heaviest elements in the universe are forged: gold, platinum, uranium. All the precious metals we value so highly were created in the collision of two dead stars. This is the ultimate proof that even the dead remain soldiers in the Cold War. They do not rest. They orbit. They wait. And when they finally meet, they create the most precious spoils of war. And what of the greatest graveyards of all? The black holes. They come in two main varieties. There are the stellar mass black holes, the remnants of individual massive stars, typically a few times the mass of the Sun. And then there are the supermassive black holes, millions or billions of solar masses, which sit at the centres of galaxies. They are the true silent killers of the Cold War. They are the generals. They command the battlefield from the centre. But they do not just sit there, they feast. When gas or stars get too close to a supermassive black hole, they are shredded by tidal forces. The material spirals inward, forming an accretion disk. The disk heats up to millions of degrees. It flares with X-ray and ultraviolet light. The black hole becomes an active galactic nucleus, an AGN. It becomes a quasar, so bright that it outshines the entire galaxy of stars around it. And this is where the Cold War takes on a truly terrifying dimension. The supermassive black hole can regulate the star formation in its entire host galaxy. It can do this through feedback. When it feeds voraciously, it launches powerful jets of relativistic plasma. These jets can extend for hundreds of thousands of light years, far beyond the galaxy itself. They slam into the surrounding gas. They heat it. They push it away. They can suppress star formation entirely, starving the galaxy of the fuel it needs to make new stars. Or, in a different scenario, the jets can compress gas clouds, triggering a burst of star formation. The black hole becomes the master of the galaxy, deciding which regions live and which regions die. It is the ultimate expression of the Cold War on a galactic scale. The black hole is not just a corpse, it is a puppeteer. But to see the full scope of this puppet show, we need to look at the most powerful engines in the universe, the radio galaxies. Centaurus A is a prime example. It is a nearby radio galaxy, a giant elliptical with a supermassive black hole at its core. And from that core, two colossal jets are blasting outward. They are not straight. They are bent, twisted, warped by the surrounding intergalactic medium. They terminate in massive lobes, immense bubbles of plasma that glow in radio waves. These lobes are filled with particles accelerated to near the speed of light. They are evidence of a feeding frenzy, a feast that has been going on for millions of years. The jets of Centaurus A are carving out cavities in the hot gas that surrounds the galaxy. They are displacing the very medium from which future stars might have formed. They are winning the Cold War for the black hole, ensuring that the galaxy remains a quiet, aging, red and dead elliptical, a place where star formation has largely ceased. This is the long game. The Cold War is not always about violent explosions. It is often about subtle, persistent, long-term suppression. It is about a black hole quietly starving its host galaxy over billions of years, slowly turning it from a vibrant blue star-forming spiral into a dull red dead elliptical. We see this in the morphology of galaxies. Spiral galaxies, like our own Milky Way, are still actively forming stars. They have gas. They have spiral arms to compress it. They are in the middle of the war. Elliptical galaxies, on the other hand, are the veterans. They are the ones who have been through the worst of the fighting. They have merged with other galaxies. They have been heated by quasars. Their gas has been stripped or consumed. They are filled with old red stars, the survivors of a war that is all but over for them. They are the graveyards of the Cold War, filled with the silent cold remnants of a more active past. And consider the role of the environment itself. Galaxies are not isolated. They live in clusters. The Virgo cluster, for example, is a dense collection of over 1,000 galaxies, all bound together by gravity. And in that dense environment, a new weapon emerges: RAM pressure stripping. A galaxy falling into a cluster moves through the hot, thin intracluster medium at hundreds of kilometers per second. That medium pushes against the galaxy's own gas, like wind pushing against a sail. The gas is stripped away, blown out of the galaxy, and left behind in long, trailing tails. The galaxy is literally being disarmed. It is losing its fuel for future star formation. It becomes a jellyfish galaxy, stripped of its gas, doomed to a slow, quiet death. The cluster itself is a weapon. The environment is a weapon. In the Cold War, even the medium between galaxies is a combatant. So where does all of this leave us? It leaves us with a universe that is a machine for making stars, but a machine that is designed to eventually run out of fuel. It leaves us with a universe where gravity is the ultimate architect, but also the ultimate destroyer. It leaves us with a universe where the smallest and the largest are connected, where the fate of a single red dwarf is tied to the activity of a supermassive black hole millions of light years away. The Cold War is a story of systemic competition, of cosmic regulation, of a universe that is slowly, inexorably using up its resources. Every star that forms is a tiny victory for gravity, but it is also a tiny step toward the final silence. Every supernova is a glorious defeat, a release of energy that enriches the cosmos but also depletes its reserves. Every black hole is a sink, a place where matter disappears, never to return to the cycle of star formation. And at the very end, when the last red dwarf has cooled to a black dwarf, when the last black hole has evaporated through Hawking radiation, when the last proton has decayed, the war will be over. There will be nothing left but a dilute soup of particles and radiation, expanding forever into an infinite, cold, dark void. But that end is so far away that it is almost meaningless to contemplate. The present is still rich. The present is still filled with the drama of the Cold War. And we, the children of this war, are uniquely positioned to witness it. We are not just observers. We are participants. Our very existence is a consequence of the Cold War. The carbon in our bodies was forged in the bellies of massive stars. The oxygen we breathe was scattered by supernovae. The iron in our blood was synthesized in the final moments of a dying giant. We are the living, breathing, thinking aftermath of billions of years of stellar conflict. So when you look at the night sky, do not just see pretty lights. See the battlefields, see the soldiers. See the generals ruling from their black hole thrones. See the runaways escaping the cluster. See the orphans drifting alone. See the graveyards of dead stars waiting to collide and create new riches. See the war itself, raging in every molecular cloud, in every galaxy collision, in every gentle, relentless fall of gas into the heart of a collapsing core. The Cold War between stars is not a metaphor. It is the fundamental process that shapes the universe we live in. And it is happening right now all around you, in the depths of space and the depths of time. The war continues, and here we are, at the end of this story, or maybe just the beginning of understanding it. You see, the stars are not eternal. They are not those fixed, unchanging lights our ancestors gazed up at in wonder. They are born from conflict. They live through conflict, and they die in conflict, every single one of them. The matter that forms our sun, this warm yellow star that gives us life, was once part of some immense molecular cloud that lost a battle, or won one. Depends on how you look at it. That cloud collapsed under its own weight, fought against the pressure of radiation, and somewhere in that chaos a new star ignited. And from that same violent process, planets formed. And eventually, us. Think about that for a second. The iron in your blood, the calcium in your bones, the oxygen you just breathed in and out without a second thought. It all came from some ancient stellar battlefield, a place where gravity, radiation, and time wage war across scales that our human minds simply cannot grasp. We try, we build telescopes and supercomputers, we write equations and theories, but really, we are just children staring at the ocean, trying to count every wave. The universe is a place of genuine consequence. Every action has a reaction. Every collapse sparks a birth. Every explosion seeds the next generation of worlds. There is no waste in this war, only transformation. This story we have walked through together is not a metaphor. It is the literal physical process that shapes everything we have ever known and everything we ever will know. And here is the thing that keeps astronomers awake at night. It is not over. It never ends. Out there right now, molecular clouds are collapsing. New stars are being born. Old stars are running out of fuel. Supernovae are building up pressure, ready to tear themselves apart. The Cold War between stars continues, silent and unstoppable, and we are part of its aftermath. We are the children of that conflict, the living evidence that the universe does not build in peace. It builds through struggle. If you want to witness the ongoing battles in the depths of space, explore the imagery from Hubble and JWST. Go look at those images. See the pillars of creation, see the Carina Nebula, see the dust and gas and light. And then remember what you are really looking at. A war zone, a nursery, a battlefield, a birthing ground. Subscribe to This Is Space to follow the war, because it is not over. It will never be over. Not until the last star burns out and the universe goes dark. And even then, maybe something new will begin. The Cold War between stars continues, and we are part of its aftermath.